has been a real challenge to the organizing committee, successfully held by Dr. Martin Puchetta and Dr. Alberto Cardona. The pandemic and its associated problems obliged to postpone the conference in 2020, and now to an atypical, but unfortunately not so uncommon these days, fully online event. So I would like to really congratulate the committee, because they handled to maintain such a successful conference with the original and current spirit of MuSMe. I would like finally to say that I am sure that most of us would like to be in Córdoba as planned, but also I'm sure that all of us will know how to take advantage of the present situation and collaborate to make from this MuSMe, this 7th edition of MuSMe, a remarkable, warm and friendly symposium that all MuSMe symposiums used to be. I wish all of you, all the participants, a very successful event. Thank you for being here, and thank you for giving me the opportunity to say these words.
Okay, so I may start my, let me see. Can you see my screen? Oops.
Okay. Yes, Marco. It's okay.
Yes, we can see it.
Okay. So the talk of today want just to clarify, beside that this symposium is focused on mechatronics, that mechanism still play an important role, mainly on robotics. I don't want to diminish the importance of synergy and integration of mechatronic design, but I want just to address this specific aspect. And the question I'm trying to attach in this short talk is highlighted there. It is asked everywhere innovation, and very often it is taught that the mechanism cannot contribute to innovation. I shall show from historical point of view the main contribution and also the challenge for the future. But we have also to understand what is innovation, first of all. And another thing that often is underestimated is how these innovation, these achievement are not only due in terms of technical means, but they produce also some other important effect in terms of community. Well, for those who doesn't know me, I am from Italy. Now I am a professor in Tor Vergata University. It's the second university in Rome. It is located just outside the ring of Rome, and we have a nice campus. You see the building, and the university is devoted to international academy, with a lot of international exchange and receiving many students. So this is just to invite our friends and young colleagues from South America. If they want to have some experience, I shall be very happy to receive them in my lab. This is some activity in my lab related to robotics and mechanism, coming from different aspects, from industrial robot, mechanical transmission, mobile robot, humanoid, even historical aspect like the last one that you see on the bottom, that is related to my interest to understand the past to better shape the future. And we have also new solution with, again, with mechanism like the finger exoskeleton you see there. Well, we know all that a robot is a mechatronic system with integration of the several multidisciplinary parts, but I may emphasize the central role of mechanical design, in particular the mechanism, considering that the a robot usually interact with the environment or human operator in substituting or supporting their action by the aspect related to motion and force. So this means that we need to carefully consider this aspect in order to better understand and fully explain the mechatronic design in the final task of a robot, and why the mechanisms are still key roles. These are the two main points I may like to stress. Whatever electronics, informatics, and the other mechatronic discipline can be evolved, we shall always need the mechanical counterpart in our system, not only in robotics, since finally any machine or machinery is aimed to help and support a human, and the human always live and interact with the environment and the object on the basis of mechanical phenomena of the human nature. So this is an important aspect that I will suggest to keep in mind, because otherwise whatever sophistication we can provide to our system, if we don't have corresponding efficiency in the mechanical component, the failure of the system is quite obvious. Well, about innovation, is a complex activity nowadays, and this scheme I want to summarize how much is complex and how many actors are needed indeed to bring innovation at the real level of exploitation. Here I just emphasize main aspect in design background, in design milestone, that are the pillars for the next step of enterprise manufacturing, for market valorization, and finally, more and more, it's getting more important, the consideration of user and public in order to really appreciate innovation and indeed to use innovation. So just to say that nowadays, we as a scientist and designer and inventor, we are still fundamental to evolve, to improve the society frames in terms of technical means, but we cannot do this by ourselves alone, and we need more and more multidisciplinary collaboration, and this is why mechatronics is teaching us a new open mind behavior. So just here to summarize that the innovation is based on this novel aspect, but in order to be really innovation, we need to make the user really using this solution, and therefore not only science and technology can be considered fundamental, but more and more education and publicity are tools necessary for innovation. And when I say education, I mean also academic frames, because we need to teach, to form young engineers who are open to understand different aspects of technology, are open to challenge their idea within even no technical frames, and therefore it's more important to have such a kind of a multidisciplinary formation in which universities still play and will play an important role. This is a message for all of us in order to be proud to be the actors in university, because not only we can create and conceive innovation, but we are the actors in forming the new generation for the future of the society, and definitely science and technology. Publicity also is very often underestimated in our frame, because we think that the science and technology is much more high than the pure market valorization. But you may understand that without publicity, you can design, conceive a brilliant solution, but the potential user, if they don't understand, or even they are not attracted to that solution, the solution remain in our desk, in our laboratory. So this is just to finally say that we need to complement, to integrate our activity with this other aspect. Coming back to our fields, here this scheme I want to emphasize that nevertheless, the science and technology still play an important role. And in this scheme, you may see that the central streamline of this flowchart is mainly based on technical aspect, and the mechanism design is a central one, which might need to be integrated when dealing with robot development, robot design, with many other aspects that are not only from the mechanics of robots, but they come from control science, computer science, measuring system, and of course, even from some aspect related to psychology, when we think we are looking to human-robot interaction or human-human interaction using a robot. The second part of the flowchart, I want to emphasize those aspects that I just mentioned in order to bring the technical achievement to the innovation practical exploitment. And for that, we need several activities that usually we are not used to deal with. The first one is the intellectual property defense. Only recently, we are asked at the university level to also produce patent and also to develop activity for technological transfer from our office, our laboratory, to outside, up to involve, to ensure the collaboration of the enterprise frame. And this means a lot of different activity which require new skills and indeed a team work. So this is also to say again, as in the scheme for innovation, nowadays more and more is not possible to make innovation on individual basis activity. And also the market valorization is it's important, as I just mentioned, and the robot service can play an important role in order to, how can I say, advertise the role of technical science of our activity, because the robot service as a new frontiers of robotics actually is not so new. We are speaking of service robot already more than 20 years. However, they may help us to attract the user attention and finally the user acceptance to bring us to the innovation goal. Well, let me show you some example from the past and the present, how the mechanism can play an important role. Here you see the first humanoid robot that was designed by Professor Kihiro Kato in early 70 and was presented in 1973 in the first Romancy, that was the first international conference on robotics. And as you see in the left side picture, the robot was evidently mechanical based. Most of its structure is based on mechanical component, not only structure, but also basic mechanism with joint and actuator and links that make the robot humanoid. On the right side, you may see the recent Larbot design that my team has developed since 2017. And as you see, there is even more evident how the mechanism play an important role. You see the legs are made by tripod linear actuated parallel mechanism, whose ankle is obtained, I will show maybe some more detail later, from a mechanism design that permit the three linear actuator to intersect in one point, and even the trunk is made by a mechanism-based solution, which is composed of a central linear serial manipulator with flexible joint, actuated by a parallel manipulator with a cable structure. Here is the details of the system, and I can show you some short video how the system can work, considering the functionality of the mechanism. Here you see the trunk that, thanks to the proper design of the mechanism of the trunk with combination of serial mechanism, flexible serial mechanism with cable actuated mechanism, can have a high payload. At the moment, our solution with a weight of less than 2 kg is able, in principle, to carry out more than 5 kilos, which is much ahead of the current robot manipulator. In this other video, you may see how the tripod mechanism can be very useful, and indeed it has been thought to combine with the trunk mechanism in order to have a high payload and capacity in the humanoid. The sketch on the bottom right is the mechanism that is used for the ankle, and at the bottom you can see the new design we are developing for the arm, because the limit of capacity of our humanoid robot is due to the anthropomorphic design with the serial chain. So we think that with a similar combination of parallel manipulator mechanism with an elbow for serial parallel, we can achieve the proper payload. Well, the mechanism can be used also in new challenging device, like in this case, we have developed this mechanism with several solutions that has been evolved since 2013, with collaboration with colleagues from all around the world, from Spain, France, from Mexico. We have developed this mechanism that is a mechanism that is used for assisting the elbow motion with a lightweight, intelligent mechanism that can be easy portable, sensored, and can give the capability of helping human men at this stage of the design is for rehabilitation purpose. And because of the COVID pandemic, we thought that the developing this kind of device, mechanical based, which can be easily understood by the potential user, is a great help in order to maintain the necessarily medical therapy home without any risk, and with the proper tele operations controlled by the medical doctor. The mechanism nature can be, of course, well modeled and exploited in with the proper formulation typical of a mechanism design. Here is just an example of the scheme of this cable driven parallel mechanism. We have the arm ring that is worn on the arm, while the forearm is near the wrist, is actuated by 4 cable. The black dot box are the servo actuator, and the formulation gives the possibility to have a suitable, efficient, open control regulation, and also with a proper control of the force that are acting on the arm under the motion assistance. So the design is based for direct kinematic modeling, as in the blue box, by expressing the length of the cable in a closed form, while the action with the wrench that is obtained by the actuation of the servo motor for the cable give the possibility to give the proper force in assisting in active, passive, or active passive mode the system. This design with cable based, since its characteristic of portability, lightweight design, and quite simple design and operation, has been further exploited also for ankle assisting motion, like in this design that we are still under developing, but with the same characteristic with the previous solution. We are using 4 cables, and we aim to support the ankle motion, either for rehabilitation or for augmentation of the characteristic. The plot give a first measure of this solution, thanks to a proper design and operation of the mechanism layout, which is nevertheless supported by the control algorithm, using proper sensor both on the system, but also on the anatomic part under assistance. So we are thinking to put not only IMU, but some AMG sensor in order to detect how much the muscles are reactivated or contributing to the motion assistance. And also we think to put some blood pressure sensor and temperature sensor in order to monitor the clinic of the limb under assistance. This is just to say that a proper mechanism design can be properly used to combine the mechatronic design. Here, from the historical technical point of view, I want to stress how much the mechanism can play an important role. Most of you know Vespa, the scooter Vespa, which is known all around the world from Piaggio. Here is the inventor. And just to start to say that behind technical achievement, there are always inventors with their personal history, with their personal constraint and vision that are important to understood in order to fully appreciate the achievement that has been brought to the user exploitation as innovation. The scooter Vespa was a great innovation after the Second World War, because after the war, in general, the family, at least in Italy, they had not a lot of money, but they still need a locomotion system. And the Vespa was a wonderful solution, because it was innovative not only in the shape of the scooter, because it was a revolutionary design, because it was not like a bicycle, but the user could be seated like on a seat and could drive the scooter like you probably knows nowadays, without any uncomfortable position like it was used at that time with other motor bicycle. But a key role of mechanism design can be recognized in the innovation due to the connection of the front rears, in which the front rear was equipped with proper spring and damper in order to make the driving comfortable. You must think that after the World War, street, the road, were not so well maintained. So there were a lot of holes. And here we just, with the student, we discovered what was the efficiency of this solution in order to recover quickly without excessive vibration, with excessive acceleration feeling by the user when they got into a hole of the road. So the mechanism was an important part of the innovation of the Vespa scooter and playing an important role to the success of the system. As I mentioned, the technical achievement and discovery are made by people, and the people make a community. The community was made on robotics once there was a quite good success dissemination of solution of robots. You may know the story of robotics, that we start to produce industrial robot and apply them in industrial frame at the beginning of the 70s. And in fact, at that time, there was already a community that was aimed to disseminate, share, and generate a new solution. And this is why we started with specific conference. The left one is the proceeding of the conference series I just mentioned, Romancy, which is the first conference in robotics, and it was organized within the early established IFToMM community, with people uniquely focused on robotics. On the right side, you see the new series of mechanism design for robotics, because now the attention has been also even more and more focused on this specific aspect I'm trying to address your attention today, that is the role that mechanics can play on robot design. And we have this series that was started in 2012, and now we are going to celebrate in 2022 our fifth symposium in Romania, and you are invited to submit your idea, your achievement, and your problems in order to disseminate, discuss, and generate new innovation also in this field. Well, speaking about our community in MuSMe, this summarizes our story. Mechatronics was a field quite mature since the beginning of the millennium, but in South America we found a lot of people interested, but not yet any forum in which these people can be conveniently met. So together with Mario and other people, so we were some visionaire in Mexico at the beginning of the millennium. We started MuSMe in 2002 in Mexico City. At that time, we had very few people. I still remember that we succeeded to attract the attention and the presence with a very impressive participation of Manfred Hiller, the late Manfred Hiller, and also Toshio Fukuda. After that, the success, as you see, we had the MuSMe organized regularly with a frequency of 3 years in several parts of South America, but we went also in Spain. This is to say that this symposium was an aggregation of people from community, from IFToMM and the Ibero-America Federation, who works mainly, but not exclusively, in South America. And this is why we have several participants also coming from Europe, from Asia, and also even from Australia. In the proceeding, we start the proceeding with CD proceedings, and now we have regularly the proceeding in the book series of Springer, with a quite satisfactory dissemination of the result, which is important for the authors. Also, we started, thanks to the plans in IFToMM, the best paper awards, and according to the rule in IFToMM, we have the best paper award in research application student. And here you can see the color picture of our community, which is fundamental by people from South America, but not exclusively from them. Well, just a few words about IFToMM. I see the president here, and as past president, I may convey an invitation to all of you to join IFToMM in order to fulfill the mission of IFToMM, that is related to promote research, development, education in mechanical machine science. With the spirit of IFToMM is collaboration, sharing, and improving the science impact and effect, not only in technology and science, but also in the society. And for that, IFToMM organize conference, meetings, provide publication frames, and help for collaboration. I want to advertise to all of you for the next World Congress that will be organized in Tokyo in 2023. And I'm quite sure that this pandemic will be solved so we can meet again and again, and first of all in Tokyo. This is just a summary of the structure of IFToMM. As you see from the scheme of our continent, IFToMM is present everywhere in the world, and the structure is made in such a way that the member organization, who are the territory association, are active with their own activity, and the IFToMM has also permanent commission and technical commission with their specific activity in terms, as I mentioned, conference and technical science initiative. And all these frames are coordinated by the Executive Council, whose president is the chair. Well, this is a short outline of the history of IFToMM in terms of generation with the different peculiarity. Today we are experiencing the fourth generation, and indeed the fifth generation is coming on with new vision, without the motivation that was characterizing the foundation and the first 50 years of IFToMM. We just celebrated 50 years of IFToMM last 2 years ago at the IFToMM World Congress in Krakow during the system. I will try to make a PDF of this presentation, and I shall post in the chat, and I'll give it to the organizer for your further reading. I want to give some more idea from the past in order to stress the role of mechanism design in technological science development, but also with effect on the science development from the past. Here I start from the Renaissance. We have three main fundamental people: Mariano di Jacopo il Taccola, Francesco di Giorgio, and Leonardo da Vinci, who, as you say, you see the date, they were one the successor of the other, and they made important achievement, important improvement in the design, but also in the culture for design mechanism and system for improving the productivity and the life quality in the society. Here just I put two examples: the bicycle by Leonardo da Vinci and the first mechanism classification in terms of joint that was again provided by Leonardo da Vinci. But I want to say that Taccola and Francesco di Giorgio, they were even more prolificous than Leonardo da Vinci himself in developing new design, in giving dignity to the mechanism design within the society with their works. They were novel machines, and even they were developing the first treatise on mechanics design in order to disseminate, but also to form young generation with the accumulated experience in design and find new solutions fulfilling the needs of the society. Well, all of us, we know James Watt. The success of a steam engine was promoting one of the main promoting aspects for the Industrial Revolution. A lot of people knows that this steam engine has a great success because of a thermodynamic cycle that was able to exploit the full energy in that process. But also the design of what is nowadays called the Watt mechanism had an important role, because thanks to this mechanism, James Watt could improve the mechanical and also energy efficiency of the steam engines, not only at the level of structure, but also of its portability. And the drawing of the on the right is an example with the first locomotive that immediately after were possible, and we started with the vehicles with a lot of power, and we can say that the success of this locomotive, most of this success is due to the fact that this is nowadays simple for barrel cage. At that time was an astonishing application of a planar mechanism made possible to widespread the technology of a steam engine from fixed structure for industrial production to mobile solution for vehicles. Well, nowadays also we have a wonderful mechanism design that has brought exceptional success. Just an example here, most of you knows the Delta robot that was designed by our friend Raymond Clavel. He just retired, and he designed this device in 1988. And nowadays there are several models of the Delta robot at industrial level and also the laboratory level for a new service application. Here I want just to emphasize the food industry, in which they are used for fast packaging of a food element. On the top right you can see the one of the most successful design by ABB, in which you can recognize how the mechanism design is the fundamental part of this very successful robot. And you can recognize, if you like, simple mechanism like a 4-bar or slider crank mechanism as a basic component. But of course, the three-dimensional design, the synergy of the mechanism in a parallel architecture, combined with proper actuation technology, control system, and sensing, make this robot one of the most successful of modern time. Well, mechanism can be also source of wonderful solution that make widespread in very different areas that can make innovation very fruitful. This is the deployable mechanism, and we understood that the first deployable mechanism were toys. This is the magic globe that in the late 90s was used as a toy, and this technology was then widespread used in more different areas, like the deployable antennas, in satellite and orbital station, but also in civil engineering or in industry, like in the right device for payload system. Mechanism can give also surprise in the history. These are two examples. One, the left side example is the famous on-court automatic sewing machine that was copied during the Renaissance, and still nowadays is source of very fantastic automatic machine. You can recognize on the bottom of the drawing a linkage design that can be interpreted in two ways, either as the first application of the couplet curve 5 centuries before James Watt achievement, or even as 2 degrees of freedom pentalateral mechanism, because if you consider that the geared system on the axle can be considered the input of the motion, and the second degree is used to give a proper input for the sewing motion. More astonishing is the Brunelleschi design for the crane, in which you may recognize a first conceptual design of cable-driven parallel manipulator. You may see on the top, on the right, you can see, let me see if I can, okay, maybe you see here now with my mouse the handle that can be considered the actuator for the cable, and these are the 3 cables that Brunelleschi used to control the pendulum motion of the payload, and also to increase the payload of the crane that was due to the gearing actuation of the top. So this is to say that the mechanism can be found in the past as a source of new idea, and the technology will help us to get a new solution. I'm going to the end of my talk in dealing with this question. During the Industrial Revolution, the scientists, the inventor of machine, of mechanism, were well reputed. And if you compare the fame of Franz Reuleaux with Dorando Petri, the first marathon winner, it's still comparable, but Franz Reuleaux, from science point of view, like James Watt, is much well recognized. But nowadays, what is the situation? How many of you knows about Ikiro Kato, Alberto Rovetta, our friend just passed away, one pioneers of robotics, Joseph Engelberg, while all of you probably knows Pelé, Rivera, or Beatles. So this is the problem for the young generation. Most of the time, the people is much more attracted by this kind of activity, which give us 1 hour of fun, while our work, our effort give a lot of much more welfare, and also much the possibility to this other guy to give us our advertise. So in conclusion, I want to say that we must be proud of our activity, and we must search to find or to rediscover the new solution or the centrality of a mechanism in order to achieve new goals, for not only for innovation, for giving better impact and dignity to technology and society, but ultimately for the benefit of the society, since as engineers, this is our final goal in our activity. Thank you, and I shall be happy to receive your comment and questions.
Thank you, Marco.
Okay. I'll try to get out from here. Okay. how I can get out the condivision. Oh, okay, here I am.
Is there any question from the audience, Alberto?
Yeah, just a comment, Marco. Very interesting talk. You raised the question of acceptance by the society of innovation. It's a real problem, and several times there are examples, and we are currently working with wind turbines, and there are examples of non-acceptance of the society for different reasons. So the question could be, how could we manage this kind of problem? What do you think? Do we have to work with experts from other disciplines in order to make an innovation really arrive and benefit the society?
Yes, I truly think, and I'm experiencing here in my small environment, that we may have a brilliant solution, but if we don't share with, I will say, proper people that very often is far from us and is far to discuss with them, we cannot make really our duty. Our duty is to develop knowledge and solution that can be useful for the welfare of people, and finally for the improvement of the society. In this respect, I mentioned IFToMM because this was the motivation of IFToMM Foundation, using technology and science for peace at that time in order to increase the welfare of people and collaboration. So I truly think that our effort should be to try to work more and more with people from other fields.
Yeah.
Even we have to maintain our identity. I'm not saying that now I will become a manager of industry. I mean, each of us has his skill, its and its capability, but we should try some more and more try to understand others, and mechatronics is a good starting point. I see also Juan Carlos Waregui.
Marco, thank you very much for your talk. Really impressive and nice. And I have a question following the previous question regarding the future. How can you comment, or what are your opinion regarding the need to understand all the interaction of robots and interaction of systems as a complex systems? How do you feel this need to new theories about managing very complex organized mechanisms, electronics, algorithms, a lot of data? Do you have any comment about it?
Well, this is also, I showed my some of my project on human motion assistance. In fact, we are working with some doctors in order to understand. Yes, we are very clever as engineers, as mechanical engineers, to use mechanical aspect of the motion. But then you may discover that if you try to transfer this, I will say not only knowledge, but your passion, your understanding to a doctor, it's really challenging. And sometimes we need to simplify our system in order to make possible that really it's understood, and then probably the complexity can be regained. I don't know, this is my personal experience.
Thank you very much.
Daniel?
Daniel.
Daniel Martins.
Just, did you hear me?
Yes.
Yes.
Okay. So, Marco, I have two questions. One is about this duality that we have between the arts, sports, and mechanical engineering, because they are like shiny activities. And when we compare, like in a car, we compare the design is over the hood. We are under the hood, we are in the engine, we are very obscure, we are in the cave, like Plato said. We are in the cave, but people are outside the cave. They can see what they do. This is one part of the question. And the other part of the question is about your experience between the academia and industry. We know a lot of tricks, a lot of deep understanding of machines on how to derive, enhance, improve, and so on. But we are mostly in the academia. So, and when you see the engineers inside the industry, they use very old tricks, outdated ones, but we maybe cannot talk with them. We do not have such a capability of talk with them, or to when you see the industry, sometimes they pay a lot of money for finite element methods to do some very small improvement on very small part of the, and they are doing that for a long time. And how do you see a possibility of enhancing and aggregating both parts of the mechanical engineering?
Thank you. You address several points that I try to just give an highlight. First of all, when I say that Pelé is more famous than Engelberger, I want to stress that for Pelé it's much more easy to get funding to start a new soccer team. For Engelberger to start a new company, he spent the full life for that, and finally he even bankrupt. So this is something we have to change in our society. And the only way to do is with the young generation. We also, I understand the frustration, because when you go to the politicians here in Italy, but in Europe in general, it's we are underestimated. They give much more money for organizing the European Soccer Championship than to organize, for example, new line of research to solve COVID very quickly, the pandemic. So this is a problem at society level. So this is why I put the question, how we can regain our reputation and impact. France Relo, and I will say in many parts in Europe, but in the world, until, let's say, before the Second World War, a very clever professor from academia was very often called to be minister of industry, ministry of university, because they recognize the quality of this guy. But nowadays, the politicians are not educated, are not even at the level they can understand what we can do for them. So I want to say, partially is our mistake. The other things, when you say our the industry is too far from us, this is true. Well, just an example. You know much better than me screw theory. Try to explain your design to even Formula One designer using screw theory. They will tell you, no, this is not. But you need the screw theory in order to conceive a new solution. So this is probably the trick. Let's hide what we use, but let's highlight what we get. This is also the problem. And this is the example of when I say how we can regain our impact. Pelé was famous because he was just scoring. He was not showing how much time he dedicated to reach the skill to score. This is probably our mistake. We put too much emphasis in our hidden activity that we want that the people recognize. We should try to be much more clever, and this is why I was addressing the question of innovation. We need to bring out from our office, from our laboratory, from our papers, the results. Of course, the result came because behind there is a lot, much more. But this is the only way to do. This is my personal experience and my vision. And I might say that with the example I'm telling to you, I'm getting some results. For example, recently, just a surgery called me, but he didn't understand what is my activity. But he said, I saw your result in this field. So this is the way we should do. This is my idea. I mean, I don't know if this is help you.
So,
No,
thank you.
it's a question for everybody, because everybody has some results, but has some frustration. So this is what you have to think together.
Yeah, this is why we have our community, our identity, but we should try to enlarge. And I think the symposium like Mechatronics, this one has been instrumental in such a way. We should be much more open, I will say.
Okay, thank you very much, Marco. We have many, to me, we have my appreciation, very famous people here, most of you, and thank you very much for your presentation. Now we give place to the students, for the young people who are looking for fame, maybe, or recognition, and we formally start the set of regular presentation. Thank you very much, Marco.
Thank you, everyone.
Thank you. So the next presenter is from the National University of Santa Catarina, Brazil. He is Fernando Morlin. Are you ready, Fernando?
Let me just change this background. Okay.
So Fernando will present 2 words, one now and then after the break. I split it to have a rest. The name of the presentation is A Method for Generating Gripper Mechanisms Using Baranov Chains by Morlin, Barreto, Piga Carboni, and Martins.
Okay. Hello, everyone. Good morning. Thank you for watching this presentation. My name is Fernando Vinicius Morlin. I'll be presenting our paper called A Method for Generating Gripper Mechanisms Using Baranov Chains. The co-authors of this work are Rodrigo Barreto, André Carboni, and Daniel Martins. We are from the Laboratory of Applied Robotics from the Federal University of Santa Catarina. The agenda for this presentation is the following. It is divided in the introduction, a review of mobility of kinematic chains, the method for generating grippers from Baranov chains, then a proposal of new grippers, and finally the conclusions. The concept of the definition of Baranov chain used in this work is the following. A Baranov chain is a planar kinematic chain with 0 degrees of freedom, where any proper subchain has positive mobility. And Baranov chains have been used in a lot of application, like structural synthesis methods, detection of improper structures, and also for more practical applications like as walking robot leg mechanisms, movable focal type mechanisms, gravity compensators. Therefore, the gripper design. If we assume, okay, is my internet unstable? Okay, I will repeat this last point. If the relationship between a Baranov chain, the main point of this presentation is the relationship between a Baranov chain and a robot gripper design and a robot gripper. If planar manipulation is assumed, that is, if lambda is equal to 3, and if point contact with friction is assumed, which is kinematically equivalent to a revolute pair, then the hand object system forms a closed rigid kinematic chain, which is equivalent to a Baranov chain. Thus, our goal in this paper is to present a simple method for conceptual gripper design based on the kinematic structure of Baranov chains, assuming point contact with friction. We need to manipulate the mobility equation in the equation 1, which is the mobility equation for mechanisms with expanded joints. The idea is to detect or to analyze the impact of the removal of links to the mobility of kinematic chain, because we have a link which will be assumed to be the object, and then this link will be removed from the original Baranov chain. And the idea is to analyze how this remotion affects the original mobility. If equation 1 is subtracted from the equation, from equation 2, we obtain this relationship, which represents this impact of removing a link from the original chain. Now we can analyze how removing a binary, a ternary, a quaternary, and so on link affect the original mobility. Removing a binary link, the original mobility will be affected in 1. That is, a kinematic chain with 1 degree of freedom will be obtained. Originally, it had 0 mobility, and then a kinematic chain with mobility 1 is obtained. If a ternary link is removed from the original chain, the mobility is affected by 3. A kinematic chain with mobility 3 is obtained, and so on. Now, I introduce this potential structure for a robot gripper with 2 points of contact. In the first picture, a Baranov chain with 5 links is represented, a kinematic chain with 0 mobility and no rigid subchains. And then if the binary link is removed from the original chain, a kinematic chain with mobility 1 is obtained, which is equivalent to a 4-bar mechanism. In the last picture, I have this potential gripper design with 2 points of contact. If a ternary link is removed from the original chain, a potential gripper structure is obtained which represents a kinematic chain with mobility 3, gripping a object in 3 points of contact. Now, the method for generating grippers from Baranov chains can be defined. It's a simple method, but it has some potential to be refined. First, we select a Baranov chain as the seed, in this case, a 90-link Baranov chain. Then we need to list the links that can be removed. In this case, 6 different links can be removed from this chain because 4 is topologically equivalent to 7, 5 is equivalent to 8, and 6 is equivalent to 9. Then we have 6 potential links to be represented as the object. Then in the list, we need to list the mobility for the possible grippers. In this case, as we have a binary, a ternary, and a quaternary link, the mobilities that can be obtained are 1, 3, and 5 from a Baranov chain with 9 links and J joints. Then we have 2 ways to follow. Or select a link which provides the desired mobility, or select every possible link and sketch every possible gripper. In this case, I have 6 potential structures for gripper mechanisms based on the 9 link Baranov chain. The fixed link, the base link has been defined, and the object has been defined. In the first example, we have a Baranov chain with a mechanism, a gripper mechanism with 3 degrees of freedom, holding an object by 3 points of contact. And in the second example, we have a mechanism with 5 degrees of freedom, holding an object in 4 points of contact, and so on. These mechanisms are both closed kinematic chains and hybrid kinematic chains because some links are serial, like in this first example. The conclusion of this work is we have presented a method to generate new grippers using Baranov kinematic chains based on the removal of specific links. Grippers can be designed using desired contact points between the grippers and the held object, and by substituting a link of a rigid chain by an object, we create a structure that doesn't have mobility when the object is being held, a desired characteristics for grippers. Furthermore, when the gripper is not holding the object, it has mobility, which is valuable for opening and closing the gripper, as well as possibly holding objects with different sizes or manipulating them. And selecting the seed kinematic chain can be a challenge, but several tools are available to assist in this task, such as variety, connectivity, degree of freedom, and actuated degree of freedom. Finally, group theory can be used to identify the symmetries of the kinematic chain, which helps avoiding designing grippers with equivalent structures. These are the references for this work. And this work has been founded by the Brazilian foundations, CAPES and CNPq. Thank you. This is my email address, and if you have any doubt, please ask me a question.
Thank you very much, Fernando. Is there any question for the audience?
Carlos has raised his hand.
Yes, thank you. Can you hear me?
Yes.
Carlos?
Hello, Carlos.
Okay, I'm Carlos from Andes in Colombia. I have a question regarding how do you select the seed of these chains in order to get the, let's say, like visible grippers?
For this example that I have shown, it was selected randomly, but we are refining this the way to select this kinematic chain, which will be another work, and a work that derives from this work. For example, we can, if we have the requirement to the actuators to be placed in the fixed link, then we can use variety to select the chain, because a chain with variety 0 has this characteristic to that the actuator can be placed in any link of the chain. Thus, the variety can be used to select this chain. Also, a desired characteristic is that the gripper is symmetric. Thus, we can use a group theory to select only chains with an axis of symmetry. For this example, we have chosen this randomly. I have shown a simpler example and a more complex example, but there are a lot of tools to select this kinematic chain. I don't know if I have answered your question. Any other question?
So, Daniel?
Well,
Yes,
that's
Daniel.
not a question. It's just a compliment that I believe he asked about the seed chain. So the seed chain is a Baranov chain that we can generate as complex as we want by enumeration process. We can generate like with 2 loops, 3 loops, 10 loops if you want. So if that was the question, this is just a compliment.
Okay. Yes, we have a large data set of Baranov chains with 1 loop, 2 loops, 3 loops, 4 loops. And so if more complex grippers are going to be designed, more complex seeds are going to be selected. And in this case, as I have these examples that I have shown, we have a simpler with 2 loops and a more complex with 5 loops. But the seed kinematic chain it is needed to be a zero mobility kinematic chain or a Baranov chain, which we need to enumerate before we go to the method of synthesizing the gripper mechanism.
Okay, thank you, Fernando. Is Aline Geronimo here? She's from the university. Daniel? No? Okay.
Aline is not here. I do not know. Fernando, do you know who presented instead of her?
Let me see in this.
Because I don't have the presentation here.
Aline, Barreto, Elias, o Vinícius e a Mônica. One of them.
Don't worry if you haven't, Daniel. We can make the break. We are, let's face it, because the long presentation and introduction of the conference. Thank you all, Andrés Kecskemethy, Marco, for introducing this conference. Thank you, Fernando, for your talk. We will do a break until 11:45, 15 minutes. Fernando will present again after the break. So take a breath. Thank you, everybody. So see you in 15 minutes. You can use this time to socialize together. The microphone remains open. The session remains open all the time. I will just stop the saving.
This paper is called The Generacy Detection in Epicyclically Geared Trains Using a Matroid-Based Approach. The co-authors of this paper are Andrea Carboni, Marina Baldicera de Souza, and Daniel Martins. We are from the Laboratory of Applied Robotics from the Federal University of Santa Catarina. This presentation is organized as follows. First, the introduction, then the method of the generacy detection in EGTs. 2 examples will be presented, and then the conclusion. For the introduction, we have the identification of degenerate structures plays an important role in the design of epicyclic geared trains, which I'll be calling EGTs. A geared kinematic chain is said to be degenerate when the links of any subchain rotate without any relative motion. That is, the links rotate at the same velocity, working as a structure that can be replaced by a single link, resulting in a kinematically equivalent simpler system. The problem was originally addressed by Buxbaum and Friedenstein, and a lot of effort has been put into this challenge, especially using graph theory techniques derived from graph theory. This paper aims to present an extension of our method of rigid subchain detection, which is based on matroid theory. This approach takes the advantage of the relationship between fundamental circuits of the EGT matroid and the and closed sets or flats of the corresponding dual. Through a series of dilation operations, the geared kinematic chain is decomposed, so each closed subchain is evaluated in order to detect any degenerate structure. This is the method of degeneracy detection in EGTs. As I said, it is an application of a more general method of degeneracy detection. I'll talk first about the exhaustive approach. In this example, first, the collection of fundamental circuits or loops is enumerated. Then the fundamental circuits are used to construct the set of all circuits, and then the set of all circuits is combined in all possible ways. This approach is exhaustive, and as the number of loops increases, the complexity of the problem also increases and it explodes. The idea here is to reduce this complexity by adopting a matroid-based approach, which is polynomial. The first case, 256 subchains would be enumerated in order to analyze every possible subchain, the mobility of every possible subchain. In the proposed approach, we have first the original graph. Then we need to construct a dual graph by placing a vertex inside each face of the original graph. Then for each pair of vertices that share an edge, another edge is added in order to connect these vertices. For example, the face represented here by the vertex 2 shares edges J, I, G, and H with the external face. Then for each of these edges, another edge is added in order to form the dual graph. And then a dual graph is obtained. This is the construction of a dual graph from the original graph. Now, for the dual graph, we need to obtain a closed subchain of the original graph using a dual-based approach. A subset of the vertices of this dual graph is selected, in this case, vertices 1 and 2, and then the edges connecting any two of the vertices corresponding to this partition are selected. For this case, if we consider vertices 1 and 2 of the dual graph, the edges that connect these vertices are I, J, R, G, J, and H. Now, it is the most important property of this work. If these edges corresponding to partitions of the dual graph are removed from the original graph, a subchain of the original graph is obtained. In this case, the partition of the vertices of the dual graph are 1 and 2. The edges corresponding, the edges that connect this partition are J, I, G, and H. And if they are removed from the original graph, we obtain this subchain. For this case, with when lambda is equal to 3, this subchain represents a rigid subchain. And in order to analyze the complexity of this operation, we can use Bell numbers, because Bell numbers count the number of possible partitions of a given set. In this case, the set is the vertices, represents the vertices of the dual graph, and then the complexity is computed by the Bell number. If the number of loops of the dual graph, of the original graph, is 4, for example, 4 is 3, and then the number of faces is 4, because we have 3 inner faces plus the outer face. Then the Bell number for 4 is 15. Thus, 15 subgraphs should be analyzed based on this approach, in contrast to the 256 subgraphs from the exhaustive approach. Now, the algorithm is proposed, the algorithm of identification of degenerate EGTs. It is the formalization of this approach that I have shown, but instead we use lambda equals 2. Lambda is assumed to be equals to 2 because we are dealing with EGTs. This assumption is proposed by Davis, and we are assuming here. Another assumption is that the mobility will be computed based on the rank and the number of joints, because matroids doesn't carry the information about number of vertices. Then we need to compute the mobility based on the rank. The rank is the number of independent elements inside of a group. In this case, the group are the group of edges. I will show the example considering a graph. I just skip this part of the presentation because I will focus in this GKC, this geared kinematic chain. Considering this kinematic chain, we need to first enumerate all flats of this functional schematic of this geared kinematic chain. By listing all the flats, I mean that we will construct the dual graph and then list the flats of the dual matroid. The flats are those edges that connected the vertices of the dual graph. For the second step, we need to verify whether MK is connected. MK is the matroid that is derived from this operation of removing the flat from the ground set of the graph of the matroid. And then we need to check to compute the mobility of the associated subchain. In this case, the mobility of the sixth flat is not computed because the graph obtained is not be connected. And for this case, no subchains with no rigid subchains are identified. The seventh step is if any subchain has mobility less or equal to 0, and the associated subgraph is a proper subgraph of the original graph, then G contains a rigid subchain. For this case, as I have said, no rigid subchains are identified for this functional schematic of a GKC. Therefore, we can conclude that the schematic chain doesn't contain a rigid subchain. Just to finish the presentation, 2 examples taken from the literature. In this case, it is a representation of a 9-link 1-DOF EGT label, 1-DOF AGT. If the flat of the dual matroid that corresponds to A, D, H, I, and O is selected, which corresponds to this partition 6, 7, and 8, we can remove this from the original graph and obtain a rigid subchain, which in this case is represented by this degenerate structure here. For the second example, which is also taken from the literature, we have a 11-link 2-DOF EGT and its corresponding dual graph. For the second example, this flat can be associated to the degenerate structure. If this flat is removed from the original chain, a kinematic chain with mobility 0 is obtained, which is associated to this degenerate structure here. These 2 examples, I am introducing them, illustrating them because they are validating the method. And I have said in the beginning of the presentation that this method is an application of another method, or a more general method that can be applied to kinematic chains with lambda 2, 3, 4, and 5, and 6. In this case, I have the application, which is geared kinematic chains, has lambda equals to 2, and we can identify these rigid substructures. This work was also funded by the Brazilian foundations. My name is Fernando. My email address is Fernando, is given here. If you have any question, please ask me.
Thank you, Fernando. Any question from the audience? Antonio?
Yeah, this may be a very fundamental question, but in slides 37 and 38, you don't need to go back there, but you did mention of those kinematic subchains being degenerate. How can you tell this? I am unfamiliar with this, but how can you tell from the graph itself that is degenerate?
I have not shown here the equation of mobility, the mobility equation, but based on the number of links and the number of joints of the chain that I obtain, I can compute the number of degrees of freedom based on the number of links, the number of joints, and the order of the space these links are operating, which is lambda equals to 2. Then I can compute using the same mobility equation here to check that this degenerate structure has mobility 0.
All right, I thought it was from the graph, but you need to go through the equation. All right,
yes,
thank you.
For every possible subchain, I need to compute the mobility in order to check if this subchain is rigid or not.
Okay, got it. Thank you.
Any other question? So let's let's acknowledge again to Fernando. Actually, we will wait for the presentation of Esdras. Esdras, please prepare. Thank you, Fernando.
Thank you.
Hi, everyone hear me? Can you hear me?
Yes, we hear you.
Okay.
Perfectly.
Thank you so much. I will share my screen.
The green button. Okay.
Can you see the presentation? Okay, thank you so much.
Yes.
Then I'm Esdras. I will present the structural analysis of the human knee in the magnetic chain. I am from Laboratory of Applied Robotics, UFSC, Federal University of Santa Catarina, and the group of this paper is me, Professor Leonardo Rincon, Elias, and Professor Daniel Martins. I will present the problem of main exoskeletons, prosthetics, and rehabilitation device, human knee movement, a summarization about this, methodology, human knee analysis, and the results. The human knee is an important joint of the human body because they support most of the load of the human body, and when you are running or jumping, the knee does most of the absorption. And we did an analysis of the main exoskeletons, prosthetics, and rehabilitation device, and we saw that the mobility is different from that the human body. I will explain in the next slide. In the human knee, you can do extension and flexion of the human knee. I mean, the rotation around the transverse axis, but when your knee is flexed, you can also do the lateral rotation and medial rotation of your foot. And this movement occurs in your knee, but the devices like exoskeleton and prosthetics just does the first rotation and not manage to do the rotation around the longitudinal axis. But this movement is important to balance when walking activity. And then we developed the methodology for analysis of the human joints. I will explain one by one with example that we used in this paper. Okay, and the left side of the slide is a methodology, and the right side of the slide is the example and application here in this paper. The first step is to do a relationship between anatomy and mechanical components. There's 4 elements in the human body that are related to movement. Bones, cartilages, ligaments, muscle, and tendons. The bones works as rigid elements. Then the bones are links. The cartilages and ligaments are elastic elements, but the difference is that the cartilage works under compression and ligaments works under traction. And the muscle has 2 behaviors. One is passive behavior and another one is active behavior. Talking about the passive behavior, the muscle works as a springer. If you stretch a muscle and do not activate it, we tend to come back to the relaxed position. But you can also activate a muscle, and in the activation behavior, it just compacts. You cannot stretch a muscle actively. I'll explain this better in another slide. Okay. Then in each joint of the human body, there's many muscles and many components. And organized way to do analysis is to separate with group of action muscles. How can we do this? The anterior muscles is the muscles that passes in the front part of anterior part of the leg. Okay? And then the anterior muscle, as a muscle just do actively the compression, and then the anterior muscles are responsible of the extension movement. The posterior muscle does the flexion movement. The medial muscles does the medial rotation. The lateral muscle does the lateral rotation. As it can be seen, you have 4 anterior muscles. I mean, you have 4 muscles that does extension of the knee. From the mechanism point of view, there is an actuation redundancies. Yeah? I will talk about this a bit more. But as you can see, you have 4 muscles that does extension. These are anterior muscles, medial muscles, and lateral muscles does the 4 balls mechanism, and posterior muscles is a complex graph. And then the links 1, 2, and 3 are the bones, and these are common in 4 groups because every muscle is connected to the bone. Yeah? This separation of action groups is important to understand how can each muscle what each muscle are doing in the joint. And then with these 4 groups, we can join these groups in just one kinematic chain. And this is the third step, generate the kinematic chain of the knee as a whole. To be clear, I separate 2 with colors, and then the anterior muscles that does the extension of the knee as the red ones, and the posterior as the blue and gray. The difference is the blue are in the upper side of the knee, and the gray are in the downside of the knee. The medial muscle and purple is lateral muscle, and in black is the bones. This kinematic chain is the same kinematic chain of this one, but without crossing. We just reorganize the kinematic chain to be clearer. And then we could do the graph of the knee as a whole. As it can be seen, we have a complex graph, but there's many redundancies and pseudo mechanisms. So the next step is to eliminate the operation redundancy. As I said, we have the 4 muscles that it's called the quadriceps. That's why it's the 4 muscles. And these 4 muscles are the quadriceps, and the redundancies in the human body is important because if one of these 4 muscles is injured, you still can do the extension of the human knee with another muscle that does the same movement. But in the robot or in the device, this is not important. Then we can eliminate actuation redundancies, and we can eliminate pseudo mechanisms as well. For example, think about your arm. We have biceps and triceps. It's easier to understand. Simplifying, when the biceps are activated, the tool will move up, and this loop is not necessary because it's not activated. In the opposite way, this muscle is important and this is not. Sorry. In the human body, this redundancy is important because muscles just operates in one sense, just compressing. Yeah, but actuator can do can operate in both sides. Yeah, and then these elder loops are not necessary. Okay, after eliminating the operation redundancies, the pseudo mechanisms of this kinematic chain, we can arrive in two kinematic chain. One with 2 loops, and the second one with 3 loops. The difference is that here we are considering the patella. Patella is a bone in the human leg that works to improve the strength of the muscle. And then we can do the analysis of these both mechanisms. Each joint is related to the relationship did before, and the red circles correspond to engines. Yep. And as we said, the kinematic chain of the human knee has 2 degrees of freedom, and there is necessary 2 actuators to control this mechanism. We can prove that there's a mobility too about the applying this kind of joints in this formula, in this equation, and we can see that the human knee is a spatial mechanism with mobility 2. Having this kinematic chain, we can do the type synthesis of the human knee and dimensional synthesis of the human knee, and to develop a mechanism that does the same movement of the human body. Then the next steps will do this and prototype, test, and optimization of the topology in order to do a better topology, saving energy. And finally, to repeat the sequence to the other human joints, like hip and ankle, to develop an exoskeleton for human limbs as a whole. We'd like to thank the CAPES and CNPq. And the group is formed by me, Leonardo, Elias, and Daniel Martins, and we'd like to thank you for the attention.
Thank you very much, Estras. Is there any question for Estras? Antonio?
Yeah, just quick question on slide 16. You made a statement saying that only 1 loop is necessary. I think this is correct only when you're considering kinematics, not if you're considering any dynamics or, say, for instance, the stiffness, because we have muscles, they can act in antagonistic way, and therefore they can change the stiffness of a specific joint, right?
Yeah. Yeah, sure. The muscles here, when analyzing this case, we have the agonistic muscle and antagonistic muscle. Actually, in this case, do you have this one operating to the actively movement, actively behavior, and this one is contributing to the movement as well. As you said, analyzing the dynamics of the movement, but you can do the same thing with just one engine. You can simulate this one, these both muscles with on one actuator. Yeah, that's why I said that you can eliminate the pseudo mechanism.
Okay, thank you.
Welcome.
Any other question? I have a question. Did you draw the what mechanism without the hinge in the middle, or just a mistake? It's fixed in the operation in the middle of the two cans.
I'm sorry, Martin, I lost you. The signal was bad. Can you repeat, please?
Yes, the hinge here is missing, or it's locked. The two links are locked. What did you draw in?
Here is locked, yeah?
It's locked. Okay.
It isn't locked. This is a revolute joint, like this.
Okay. Any other question? Let's thanks Estras again. And can we go to the next presentation? Thank you, Estras. Thank you very much.
Right.
Tiago, let me check. Tiago Weltegenbau is here.
I think Thiago is not here.
Okay. So we can continue with Lucas Bernardon Machado. Lucas sent me the YouTube link, but if he's here, please, Lucas, share your screen.
Okay.
As I know, it's your first presentation, so
Yeah.
quiet, be quiet, relax. The audience will understand. So the presentation is about the analysis of a proposal for a self-aligning mechanism for Cartesian rods in greenhouses by Lucas Bernardo Machado, Antonio Carlos Valdiero, Enrique Simas, and Daniel Martins. So let's start, Lucas.
Okay. And hello, everyone. My name is Lucas Bernardon. I am a regular master student in the postgraduate program of mechanical engineering, POSMEC, at UFSC, and I integrate the robot laboratory lab. And today I will present my article, which was published at the 7th MuSMe, was titled with analysis of a proposal for a self-aligning mechanism for Cartesian robot in greenhouse. And the authors of the present work are Lucas Bernardon, João Gabriel Dias Camilo, Antônio Carlos Aldiero, Henrique Simas, and Daniel Martin, all affiliates of the Federal University of Santa Catarina. And the use of manipulators in agricultural
3, 2, 1.
In agriculture has grown significantly, a fact that is directly associated with the improvement of operating conditions, this guaranteeing new standards of efficiency and agility in activities, both planting and harvesting agricultural greenhouse. Thus, the operations and manipulations cited can be represented by the following GIFs, where we have a kiwi harvesting robot and autonomous robot for pesticide application, fertilizers, and weed removal. Well, gantry Cartesian robots have 3 prismatic joints, resulting in a movement composed of 3 translations, whose axis of motion coincide with a Cartesian reference coordinate system. That is, we have 3 DOF, degree of freedom of work and operation. Such a mechanism operates in a suspended manner in relation to the ground, and ideal for optimizing the working space and operation inside greenhouse. In figure 1, we have a representation of a gantry mechanism. In figure 2, it's the workspace. This work studies the main movements, mobility, and self-alignment of a Cartesian robot during its operation in protected cultivation, since the robot moves through linear grids, rails. The main objective is to develop the self-alignment analysis of the moving mechanism, where mainly are analyzed components of the rails, the pulleys, and the robot's chassis. In this slide is the true justification and motivation for the development of the work in question. We have my first project as a mechanical engineer and a climate hydroponic greenhouse where crops are grown on banks without direct contact with the ground. The greenhouse has control of climate parameters such as air humidity, temperature, wind control, and lightness. And the project was installed in the city of Olambra in São Paulo, which is now the capital of flowers, a city that has the highest percentage of greenhouses in Brazil. For the analysis and development of the work in question, it was necessary to determine some restrictions and design requirements, and directly linked with the constructive and operational aspects of the greenhouse, in accordance with the table 1. And in table 1, we have the main structural requirements for the greenhouse and the functioning of the mechanism. The structure in which the analyzed mechanisms move is shown the figure below, where the rails irregular that is on non-linear trajectory are located at the top of greenhouse, thus composing an irregular path to be traversed. In figure 1, we can perceive the structure in which the mechanism will be coupled as for example, the irregular rails and indicate in the figure, and the movements carried out by the robot. In this case, there are 3 translations in relation to the Cartesian coordinate axis. In figure 2, we have one more representation of the mechanism. Therefore, the mechanism is composed of 6 links and 8 joints. The movements of the pulleys in relation to mechanism are indicated in the figure. We also have a representation by graphs, where we have 3 independent circuits. Circuits 1, A, B, E, F, circuit 2, C, G, circuit 3, and D, H. The Reshetov method aims to help the problem in the figure below, where there are restrictions on the displacement of the pulleys in relation to the irregular track, since they were designed to satisfy the ideal conditions of the linear track. In figure 3, then indicates the mechanism used for self-aligning analysis, where the main problem represented in this placement of the pulleys in relation to irregular rails, which many times cause the system lockout. So, and according to the previous figure, it's possible to assemble the Reshetov table. Each independent circuit makes up a table as indicated in the figure and in the graph on the right. Well, our rotation and translation movements generating were distributed, resulting therefore in our mobility and restrictions of the gantry mechanisms. Remember that excessive rotations can turn into translations on a distinct axis. Finally, according to the Reshetov method and step-by-step described in Tesai's book, it is possible generating it's possible to generate a new concept of the mechanism already self-aligning. And thus, it was necessary to add a prismatic joint allied with a rotate joint. Sorry. Rotating joint, as shown in the yellow in the figure. Therefore, the mechanism is able to move over irregular rails without compromising the system operation. In this slide, we can see a modeling of the developed mechanism and is the workspace inside the greenhouse, where the greenhouse and robots operation dimensional parameters were taken into consideration. In figure 7, it's possible to see structure of the mechanism in isolated way, where we have its entire structure coupled in the agriculture greenhouse, thus carrying out our operation in a suspended way without compromise the safety and efficiency of the activities. This paper presented an analysis of mobility and restrictions of a new manipulative mechanism for a agricultural greenhouse, used for the most diverse activities in protective cultivation. The use of a self-aligning mechanism for a greenhouse allows the constructions of prototypes with low costs not complex assembly and adequate precision. The Reshetov method was used, which in turn proved the existence of extra mobility in the mechanism and in the respective redundant restrictions. Based on the problem, it was proposed some changes in joints of mechanism in order to eliminate redundant constraints and the wanted mobility. Here are some references used in the preparation of the article. Thank you for attention of everyone who participated in this presentation, and thank you very much.
Thank you, Lucas. My question is, if there is there any industrial partner interested in your development? Daniel?
Well, not now. We are starting a new field in the agriculture mechanisms, and we are talk with people in this field. Lucas has worked on this field exactly and has noticed. Lucas, please put slide 7. Yes, and he did work on this greenhouse for flour. We have a huge production here of flour in in Sao Paulo, in Paraná, in the middle, and the irregularity of the rails was present everywhere. So this was an initiative from Lucas from working on this field, and maybe in the future, because he is starting his master's degree here, so maybe in the future he will contact his ex bosses, but. This is one comment, and I just want to add one thing, that is that the irregularity is quite common in this field and make the working improperly. And for my comments, I have the situation. Put number 10. Number 10. This is the Reshetov method. This is the core business that he did work. Is a very old method from Russia, from Leonid Reshetov, and it's quite useful for looking at those red lines that I say that go to hell, that's over constraint. And whenever we can have a complex system and you have those over constraints mapped, so we can look properly on how to solve and how we can, whenever we put some degrees of freedom, just put one next, Lucas, 11. Yes. So it's quite simple to solve, but whenever you have the map, and then just adding properly one revolute joint and one prismatic joint, this system becomes a lot more flexible and a lot more adjustable to work properly, even in half situations like in the agriculture. Just to add some comments extra. Thank you.
Daniel, my question is for you and Lucas. The Reshetov method assumes that one of the rail is straight. Here, for instance.
The Reshetov,
You're assuming that this one is cannot absorb the reflections?
No. Well, no. It's in effect it could be put on the other if you want. Just that one. The problem is that we have like 4 rails, like a car. We have 4 points of contact, but 2 will be more properly situated there. They can rearrange. But whenever we rearrange this, the parallelogram, it's out of sight. So going out one way and the other way. And whenever this common greenhouse gantry robots, they do not call gantry robots, but they are Cartesian robots as well. Whenever they have such errors or non-linearities of the rail, so they tend to push aside, and then the force simply stop the movement. So Martin, we can put on the front or on the back rows, because in fact in this field they go up and down, and
it's relative.
Yes, I do not know if this was your question properly. Sorry.
Okay, thank you, Daniel. So if there is no any other presentation, because Tia was not presenting, we will go to the break. Thank you, Daniel, and thank you, Lucas. Thank you very much for your presentation. Thank you, Fernando, and Esdras. And next, after the break, 13:30, 1:30 is my presentation. So we be waiting for you. Thank you very much for being here.
Just confirm, it's 1:30. Okay.
Yes.
1:30. Okay.
1:30.
Okay. Thank you.
See you, Marco.
This presentation is mine. It's the work published in the 2020 book. It is about the synthesis of hybrid flexible mechanisms using beams and spatial design constraints. Can you hear me? Somebody confirm me. Hello?
Yes, we can hear.
Thank you, Alexander. It is a work developed by Alejandro Gaston Gallardo, who is doing his PD with a CONICET fellowship. So the first motivation is about the use of parallel flexion mechanism to reproduce another mechanisms which are composed by beams to take. Also, it is motivated by the 3D printing manufacturing technique that allows to print flexible parallel mechanisms more easily than just 4 or 5 years ago. All the multi-layers micro electromechanical system and micro optical electromechanical system are also of interest in platform with few degree of freedom, the rotation and translation, or 2 rotation and 1 translation, which means in the terms or the field of the micro arrays, the piston, the translation is the piston motion like this is the vertical motion out of plane. 1 rotation or 2 rotation, it depends on the application in optics. Optics, the light phase modulator, phaser array, laser beam steering for low energy and very high energy also. So for very high energy laser beam steering, it's more adequate to use a parallel flexure platform than this multi-layer or 1-layer micro arrays. So a second challenge is to put it off the device like array. This is a 1-directional array, but there are also 3-dimensional like in the next presentation. So from the mechanical point of view, we need to convert or learn to this design to evaluate the feasibility to design parallel flexure platform and also arrange it in rows and several ways, geometrical ways of arrangement. And for arrange the platform, we need to satisfy also a special constraint. So the problem could be so easily done. This one, the piston motion and rotation, tip piston motion. But if we design the trivial solution or the first solution with orthogonal beams, we get this solution with beams in blue. But none of these solutions satisfy the possibility to put all the beams inside a box or below the mirror to arrange the array in several ways, in array in terms of one-dimensional or two-dimensional arrays. So we use the freedom actuation and constraint topology to design parallel flexure. It is based on screw theory. Using screw theory, the design is more simple and also accurate. At several scale, it can use the meso scale, macro, meso, micro, and also it is used for other researchers at the nanoscale. The screw that we will be interested on is the screw line. The general screw has the direction vector S along a line. This line has a moment which is taking an origin. We take the vector, the distance vector R or the location vector, and the product, the cross product with between the location and the direction give us the moment vector. So the moment and the direction is compose a screw. When there is a pitch, we have a general screw, so the moment vector is shifted so like S supra 0 is not orthogonal to the line anymore. So for a line, we have the direction and moment, the dot product is 0, but this is not true for a general screw. When there is a pitch, we have a moment which is not orthogonal to the direction. We are looking for a parallel flexure composed by beams, only for beams which are lines. So we need to study all the line screw system, or the wrench system must be composed by independent lines only, without any couples. And if there is any couple, or the moment, we must transform it in line screw. So the convention is very useful, really used for many other researchers. The direction vector for the twist is the rotation, and the translation is the moment of the rotation plus the pitch times the magnitude of the rotation. For wrenches, the direction is given by the force, and the torque is the moment of the force plus the pitch times the force, which is the complete moment of the wrench. The reciprocal product is the product crossed, the moment of the wrench with the the direction vector of the wrench with the moment of another screw, in this case the twist. This is a work, and this also the translational work, and the other terms is the rotational work. Using a swapping matrix, we can put it in matrix form, but the reciprocal product it will be used also to compute or to evaluate the feasibility to build all the parallel flexure with beams. Given the freedom space, which is a set of twist vectors, all the twist, decided twists. In this case, the twist representing this translation and this rotation are the twist vector of dimension 2. Will give you or will produce a range system constraining that parallel flexure with dimension 6 minus 2 for that example. And it is very easy to compute using the null space or the transpose of the twist system, which is the complementary or reciprocal space, W. So given in a synthesis problem, we need to provide the motion, the decided motion, and then from that unknown and the space, we compute the ranges and try to design all possible arrangement of beams that produce this constraint. So we will see the range system as a set of column vector with all the range. We need to evaluate if this range system can be built only by line screws. This could be contained forces and coupled screws, pure coupled screws, but we need to evaluate if we can transform it. Using the blending second-constraint rule, it is very easy for engineers to build parallel flexures. So the beams are assumed to be flexible in direction perpendicular to the point and rigid in extension. We assume this hypothesis for the beams, and it is useful to constrain translation. For instance, if we need to constrain this translation, we put the beam in the same direction, connected to the rigid body. And for rotation, we put also the beams perpendicular to the rotation axis. So the beams allows this freedom and allows another more freedom that will be shown later. But the translation allowed can be considered also as a rotation at infinite. This translation would be considered this rotation at infinite distance. So these are the rule points on the axis of the body rotational degree of freedom will intersect all constraints applying of the body. A more complicated mathematical approach, but completely close and is easy to follow. Up to some step is systematic. For instance, from the rank of the direction vector, only the direction of the range system, we know using several theorems that the rank must meet 1 for if you have 2 or 3 direction vectors. For instance, 2 or 3 parallel lines, 2 parallel lines in space are in the same plane, generates a plane, and the third one are all of rank 1, all parallel, but when you put a fourth line parallel to the other 3, we have rank 2. So for instance, what happened with n2 of n, 2 and 3, and n equal to 4. After some combination, we will see if some general screw can generate all the space. We combine the range system to produce a general range. We compute the cell reciprocal product of the range space. After some mathematical burden, we can find that we compute this one in matrix form, and after the Ishimbalin decomposition, we must require that that matrix should be indefinite to have a solution to be all line screws. These are the force part and the moment part of the ranges. These matrices and could contain, as I tell you recently, forces and couples. If the matrix is indefinite, this is a necessary and sufficient condition to have a parallel flexure system composed only by line screws. After that, using this eigenvalue, we can put in this quadratic form to evaluate if there is m coefficient for the combination of this range system. If there is so, we also need to avoid to check if the direction vectors are not trivial and are not null. So after that, which is very complex, we can compute this line in blue from the complementary space of the twist space. So that's the process. This is the screw system is formed by the twist. The complementary space is computed to compute the range, and the range system should be evaluated to build the beams only if it can be considered, it can be converted in a line screw system. If it is not a line screw, it cannot be converted in fully beam. So this is the range. Each beam has this twist with 5 freedoms, the 3 rotation and translations, except the translation along the beam, which is the unique range of the beam. By combining this beam, we can constrain more and more degrees of freedom to form parallel flexion mechanisms. We use also the graph theory representation. It's not a standard, so Gaston analyzed many mechanisms. He take the main idea from Frederick Soon from the University of California. This dot or vertex in the square is the stage, and in the rounded is the ground. The intermediate body, like this one, between the ground and the stage, are labeled with B. The stage could also be connected directly, constrained to the ground. For instance, here the stage has 6 beams and another part of bodies, flexural bodies, to actuate it. So some bodies of flexure are used to constrain and get the degree of freedom, and other, this is E7 is the constraint, the 6 beam or the constraint range, provide the constraint range, and the other parts provide the actuation. So that here, in this case, the actuation are decoupled. We can actuate individually the body to get some decided degree of freedom or decided motion. So the next presentation will be about this complex case, and I will talk about a more simple case, in the planar case. So in the planar case, in the planar, this could be a planar motion of the stage, but the mechanism is in 3D dimension. So the twist again, this is a translation, rotation in X axis, and this is translation in Z axis, theta. The reciprocal space can be easily computed. It's a complementary space to the twist. And using beam, we can convert these two forces. These are forces in X and Y, and these are moments with a moment My and MZ in theta. And we can convert it using the procedure into all line screw. For instance, line screw in X direction, another line screw in X direction that constrain a moment around the X-axis, and another beam in Y direction. This is X, Y, Z, and the direction part, and this is these three are the moment part. And we compute along the y-axis, but we shifted to provide this moment, a moment around the y-axis. So we constrain this. These are completely equivalent. This has forces and couples, and this has only forces. Forces around the beam direction. So this can be realized as a screw line system. So the main difficulty of this arrangement, we would put another direction. We cannot provide this constraint. So, for instance, to satisfy the space, we need to have set direction for the beam, and we violate the constraint space. So none of the beam has the component in zeta, in the set direction. So one solution to evaluate more alternatives is to include a serial parallel platform, an intermediate body, and try to put mechanisms here between the intermediate body B and the stage and the grounded stage. So using the same approach, a translational couple cannot be stratified. So the second option is transform the twist system in two rotations. At a rotation in the direction X, let me show you in this next figure. A rotation E1 and a rotation E2. Each one shifted an equal distance from the origin in the Y direction. So this motion will be performed between the intermediate body and the stage with this 5 beam. This is 1 degree of freedom. We need constraint 5 degrees of freedom with this beam. These are the reciprocal space to this motion. And for the other rotation, this is the reciprocal space. And we need to evaluate how to convert this one, which have couples, into beams, which are shown here, the blue lines. These are the conversion. It is possible because we satisfy all the conditions to convert it in line screw systems. The line screw system are all the beam in blue, and this one is this one. And all satisfy the blending rule. All the beams are concentric with the rotation axis. So in the simulation, we will see in the plane Y Z, but they are three-dimensional. So we evaluated with finite element simulation. Here we rotate the beam here, and it rotates around the E1, this axis, and when we outside the intermediate body, it rotates around this axis. And the combined motion produce, look at this, zero translation here, a pure rotation around the Z axis, the X axis, and also piston motion translation can be computed using the screw, obviously, using the algebra of screw. We compute the forces to produce a given translation. So these are the actuation points, and combining the direction pulling and pushing, we can produce either their pure rotation, pure translation, or a combination of both. So this mechanism satisfies the space, the spatial constraint, and can be arranged also in many other mechanisms. So the problem is later to evaluate how to actuate these designs. There is some asymmetric motion here. We will see, for instance, that when we produce the piston, there is a parasitic motion here. So we also evaluate if we can compensate the parasitic motion when we have a piston motion, for instance. To avoid that, we try to use a symmetrization. So we build the same mechanism, symmetric, but also satisfying the space. And we face another problem. So we could design, following all the procedure, enlarging the graph with these intermediate bodies, which are equivalent. The motion are the same. This and this one have a center of rotation here. These two beam and these two beam have a center of rotation here. So A1 and A3 are equal, have the same motion. A2 and A4, these are twist systems. They are not motion, simple motion. They are twist systems. So the intersection of the motion give the decided motion. E1 plus E2 that give you the tilt and piston motion. So this is completely equivalent in terms of motion, but we have this slanted additional flexibility here, which is not good for the precision of the platform. But it can be completely solved if we enlarge the base of the ground. So if we enlarge, they are more separated, and the accuracy improves. In the rotational motion and translation was evaluated and measured in the finite element simulation. So the finite element analysis give us similar. All are very accurate, but the more accurate are this one, the symmetric solution, where the bodies intermediate are actuated. So we can actuate these intermediate bodies instead of the platform. So it is an advantage to put the platform, the actuator far from the mirror or the another point of interest. So these are the main results up to now, and we were looking for better application and construction. So, here we can see when the way of actuation in the state change the accuracy of the system also. So we will work on construction of range systems so that can meet spatial constraints. That's our contribution here. Some systematic pegs are remnant, and still we are using blending rules and an open issue that deserves further investigation to make it fully automatic. And the process was used for an RT platform. It cannot be meeting the constraints, so we resort to two parallel flexuring series and a more complex symmetric version with the couplet actuation and the intermediate bodies. They was validated using finite element, and the series version made the partial constraint, and the symmetric version is more accurate. More accurate, but as the bus base was enlarged, it violates the partial constraint. So the series version is the best. So we like to acknowledge the fellowship of Alejandro Gallardo in CONICET. Thank you very much. Some questions? Daniel?
I have a question. It's just a comment. When I did like the way you integrate the graph with the screw theory. Beyond the fact that most people that use this do not tell that it's screw theory in itself. Hopkins, I do not know, but blending do not tell directly that is a screw theory. But one question that I have is on the graph, is exactly on the graph. Show me, yes, this one. I use this notation. You say the actuation body. I understand the actuation body is the body that receives the force or the range, the extent. Yeah,
yes.
But I believe that well, it's opinion. Just I was wondering about it. That in fact the actuation is at the joint level. It's in fact is like it is on the edge, not on the body, because it's like you can imagine that you have like a spring that connects the ground body to the end effector or something like that.
Yes.
And then
Yes.
the actuation is there. And maybe, because maybe this could enhance a bit on the graph representation. This is one question. Well,
Yes, it's true, but we actuate the body here. Yes,
yeah.
When we look with traditional linkages and other mechanisms, we consider that the actuator are rotational joint or translational joint. But here in the representation, the actuated body are those bodies that receive a general range in any direction. It could be force and run, like this one. This receives the forces here and here, and it is not a joint, it's a rigid body. But there is a relative twist between body,
yes,
rigid body, and rigid body.
that's what I mean. Because the problem is that in this situation, like the third one, well, the third one is not as complex as it is, but imagine that you can have like between two of this body, two G's or two B's, you can connect by such an actuator, like a spring or something like that. So this would be, my feeling is that this is quite interesting, just a suggestion, because most people that work on this, they consider just two kinds, a serial, that is completely serial one, and the completely parallel one. But there is lots of things in between, because there is some more complex mechanism in robots. And if you consider such a kind of generalization, maybe you can enhance this and you can join these two worlds, the world of screw theory, classical screw theory, and graph one.
There could be kinematic pairs, for instance, between two beings.
Yeah, like this one.
For instance, and this will be the more general case in the theory.
Yeah. I understand. No, it's just an idea.
Chain. There is no kinematic chain, but you can combine the kinematic chains and use the graph theory conventional, which would be a kind of dual. Yes, it's true.
Yeah.
Here it is completely.
And I have a second comment, because whenever you find the range that is the equivalent range, you can only apply force, because it's rare to normally you have to find the elementary force, and then maybe you can generate a flexure and so on that generates some moments and so. But this is like a limitation that you have in this kind of methods.
Yes, it's a limitation.
It's a limitation. Okay, just a curiosity.
It's a limitation, and I will show you in my presentation how to flexibilize to blend blades, but it's also limited. Let me show you. Sorry. So there is more question about this presentation. Is there any question? Thank you, Daniel. I will continue with the next one.
Sorry, I have just a remark, not a question directly. As you are chairing the session, Martin, just asking you if all the presentations are to be presented today, the next ones, because we have to move faster. I think we have only 1 hour. Just a recommendation.
Yes.
Okay.
Yes, I will go faster with the next one. Thank you for the appointment. So I will quickly present the next one. B. It's okay. So it is similar with another motion, tip tilt piston. It's the same approach. The tip tilt piston are more complex and need to be arranged to form micro mirror arrays. This is designed for only one, for high energy laser beam steering, and can be built in a monolithic form to be built by CNC machines. So these are examples. It's the same concept that recently. The wire and blade are similar. With blade, we can constrain two forces and one moment, and have two rotation and one translation, using beams also. So we are limited, as mentioned, as pointed out, Daniel, with beam, but here we can build blades also. So it's the same process. We identify the design motion and constraint, represent the topology by graph, analyze the freedom phase for every path from the ground to the body, and compute the physical implementation of the twist resulting between the paths. And in this case, this is the twist and the range, and these are the beams for this one. And we analyzed some proposal by how, using our graph representation and partially by developed by Sun and Hopkins, we take the same design constraint to try to design another concept. For instance, this is more simpler concept. Let me show you. The orthogonal rotation of the tip tilt was changed to a hoop of rotation. With this hoop of rotation, we can combine it. It is equivalent, this twist to this twist, this one and this one, and this is more easy to design. That's our main contribution here. So using this design, as recently we split it into rotation here in the plane case. In the three-dimensional case, the disco twist can be represented by this one. The direction are separated 120 degrees. So it is a more complex analysis of each path to design and find the sequentially, step by step, the twist using beams. So these are the steps between the beams. Also, the more complex part is that the beams to obtain the rotation. For instance, this two beam constraint allows, a rotation here. Two beam constraint. The same concept are used symmetrically, but the intersection of the motion eliminate one degree of freedom that is overdetermined. So computing all the step here between the intermediate bodies and the stage, we can design the beam. So the analysis of the beam later will be more simulated to obtain a rotation in x-axis, rotation in y-axis, and the piston motion. The same for another more simple design. This design have blades for the structured body. This also has the same, but in this case, this one are an additional constraint of beam here, a redundant constraint. So that's the same methodology applied recently was used here. And also we can replace beam by blades. So we get more easily to manufacture designs but they are more stiff, and complex to actuate. So these are the conclusions. We follow all the study in the first year of the MuSMe was continued for the 3 decades in the present year. So we designed 2 parallel tip-tail piston. The actuator change here. Here the actuators are vertical, parallel to the piston motion. And here, in the other case, sorry, the actuators are in the plane, in the X-Y plane. These are all horizontal forces on the planes theta y. And we will study intermediate actuator if we to get some better design. And that's all. Thank you. I once told more time for the other presenters. Sorry for extending it. Any question? Yes, Mario.
Yeah, very fast question and very general. And I would like to you to forgive my probably basic question, but is there any other way? Very interesting to use string theory and the way you solve the problem, but what are the advantage of using zero theory to solve the problem you are facing? I mean, if you can just give a general comment.
The main advantage is that you are manipulating mathematically rotation and translation. Like this complex crude, like I explained in the first slide, when you are used to or get used to manipulate mathematically with linear algebra theory, you really can solve very complex systems. And that issue, for instance, if we can put beams or not, it can be determined using linear algebra. So the eigenvalues tell you if there is a solution, or linear reduction by row tell you if they are linear dependent or not. That used in robotics for kinematics or analysis of Jacobians or loss of degree of freedom, they are using screws. The Jacobian are the screws. So in this case, the screws are very advantageous. If you use Cartesian coordinate, you can really solve that problem. Unless the robots are very simple or reduce the problem, like delta robot, like some very few typical robots that make everything easy in 2 ways, in Cartesian or screw. But a Q theory may help you to solve more complex in a simpler way, more complex design.
Okay,
yes, I say one more compact and elegant, but it's not only elegant. We are understanding after 2 or 3 years, we can understand which are the main advantage of reciprocal product or linear independence of line, and it's worth to study field theory. Thank you, Juan. So let's talk. Let me see the program. Are you ready? Maybe it was here. Can you present? Maybe Romero is here.
Nader is here, but I believe he sent he is in Colombia. He has an issue with the internet. I believe he sent
yes, he responding today.
Yeah,
Rodrigo Barreto
he
del
sent a
Piero.
video. He sent a video. I have the link here. If you we can.
Please.
Okay, just
you can...
it's a YouTube link. Let me get. Have you sent?
Share the screen and put the video. We will make the question to you.
Have you sent on chat? Just this one.
Daniel Rodrigo is here.
Martin, if you can, because.
Okay, I will share the screen and put the video.
He sent a video. He is online, but the connection is really bad.
Other vehicle with 2 steerable axles. This research was done by Bruno Felipe.
So we will hear the presentation of Nadir Romero. Dimensional synthesis of 2-axle steering system with Bruno Buzzi, Nadir Romero, Daniel Martins, and Rodrigo Vieira.
Hello, everyone. This presentation is about dimensional synthesis of a steering system of 3-axle vehicle with 2 steerable axles. This research was done by Bruno Felipe, Daniel Martin, Rodrigo Vieira, and me, Nadir Romero, in the laboratory of Applied Robotics, Raúl Gender. With the aim to enhancing the maneuverability, we propose a vehicle with front and rear steerable axle and middle fixed axle. For this configuration, the Ackermann condition can be expressed as cotangent of front outer steering angle minus cotangent of front inner steering angle is equal to W over L1, and cotangent of rear outer steering angle minus cotangent of rear inner steering angle is equal to O over L minus L1. The idea is to synthesize 2 4-bar steering linkages to approximate the Ackermann condition. For this, we use the Fredholm equation in order to derive the synthesis equation. The Fredholm equation relates θ2 and θ4, where θ2 and θ4 are functions of delta I and delta O, respectively. A and beta are the same variables. Now, the objective is to obtain a polynomial system equation that is possible through a chain of variables where the same variables A and beta are changed by X and Y. The coefficients A, B, C, and D are constant that depend on the steering angle. To obtain an optimal solution, we can minimize the sum of the square of the front and rear synthesis equation. The indices of F and R indicate the variables of the front and rear axle, respectively. Rho is the ratio between L1 and L. The proposed model was applied to a vehicle with dimension wheelbase equal to 4.3 meters, front track equal to 2.13 meters, and rear track equal to 2.17 meters. We'll find the optimal values of the same variable of FF, YF, XR, YR, and Rho. From this artificial variable, we can determine the variables A and beta for the front and rear axle. The connection of the front and rear steering system is done through gear with transmission ratio equal to 0.33. Here, the figure shows the comparison between Ackermann and the front optimized 4-bar linkage. And here, the comparison between Ackermann and the rear optimized for barrel cage. This figure shows the error of front and rear steering system. This error is due to the relation between delta IR and delta IF. Finally, the conclusion of this work are the following. In this work, a procedure for the dimensional synthesis of the steering mechanism with two steerable axles was presented. This formulation also opened the possibility of exploring analytical solutions because the synthesis equations are polynomials. The results obtained after optimization show that vehicle using this work would have adequate behavior with the dimension of time. Thank you.
So, thank you, Daniel. Any question to this work, for this work?
I can answer if there is any question, but maybe neither if the...
Is there neither? Is here? Okay.
He is, but the connection and the audio is terrible, so...
Okay. I understand everything. It's very clear, the approach.
Okay.
And the analysis. And what are the main motivation of this one? Cars with front steering are commonly used. Cars with rear steering was presented in last MuSMe by the group of Peru. And this one is front and rear steering.
Well, the motivation is that we do not have enough trains in Brazil. So most of the cargo is done by huge combination, and you have a huge variety of those combinations that are destroying our roads and destroying everything here. And they have lots of issues when doing the yes. So what is occurring is that people want to have more axles in order to carry more load. This is one, but they want to be to do this as cheap as possible, and they simply do not care about steering. So they destroy the tires and destroy everything, and so there is a need for this. And we had an engineer that did work with those companies that create such a kind of truck combinations. And this was the motivation that we did. And the other motivation, the theoretical motivation, is that the Freudenstein equation is quite an elegant equation, and to have to combine them in 2 or 3 or more, it's not so commonly found in the literature.
I was finding useful for mobile robot with high payloads.
Yeah, this is the
we
same.
We design a lot of from robot with differential motion here in Cordoba, with differential wheels, but with that double steering, we have a higher maneuverability.
Yeah, that's
you can explore the configuration space,
and including you have to couple the roads, because sometimes you have to have extended road in order that a huge truck could do the maneuver. So some roads, some kind of trucks cannot do. And if they have such a kind of double, triple steering system, steering axis, they can handle the situation.
Okay, thank you. Any other question for Daniel?
I have a question. What about the stability of this kind of kinematics for a vehicle?
you are saying stability in
the vehicle stability.
This is there is a ex-student of mine that's professor in Colombia in Pamplona, University of Pamplona, Gonzalo Moreno, and he did his work on the stability, because this is a crucial part, because most of the stability systems that consider just like a block that you have like the factor of stability depending on the height of the center of gravity and the track width. But when you have lots of tires, whenever some tires lose contact with the ground, the system initiates an unstable motion, and then starts the rollover. So we had a work with this. I can send you the PhD thesis to you if you want. It's a quite complex issue, but the stability is on another plane. It's a normal on the transversal plane, and this is on the
okay. Yeah. Thank you.
Thank you, Alberto. Thank you. We acknowledge the presentation of Daniel and Nader. So the next presentation will be Barreto, but it will be presented also.
It will. Fernando Morlin will present. We could.
Fernando? Okay.
My screen is being shared, right? So, can you hear me well?
Yes.
Okay. Sorry for
yes. We can.
Sorry for any background noise. This work is called the type synthesis of gripper mechanisms using Baranov chains and Davis method. My name is Fernando Vinicius Morlin. I am the second author of this paper. The other authors are Rodrigo Pereira Barreto, Andrea Carboni, and Daniel Martins, and we are from the Laboratory of Applied Robotics from the Federal University of Santa Catarina. The agenda for this presentation is the following. We have the introduction, then a brief introduction to Davis method and Assur virtual joints, the development of new gripper mechanisms, and then the proposal of new grippers, and finally the conclusions. This paper is a companion paper of the work I have already presented, and where we discussed a method for structural synthesis of gripper mechanisms using Baranov chains. The approach here takes advantage of the approach of that paper takes advantage of the effect that the removal of a given link has on the mobility of a Baranov chain. Here in this paper, we aim to present a method for defining the joint types of those generated mechanisms using for this Davis method. Then we have the concept of a Baranov chain being used to generate a gripper mechanism. Here we will define the type of these joints that form the mechanism. Then thus the type synthesis method is used to generate a couple of potential gripper mechanisms based on a 9-link Baranov chain, which are functionally represented for a better understanding. Now, a brief introduction to Davis method and Assur virtual joints. If you're not familiar with Davis method, this method is based on screw theory, graph theory, and Kirchhoff laws. It is performed by, in this method, we perform a static modeling. A static modeling was employed. Each constraint is modeled by a wrench, which is a screw representing a force. The mechanisms are represented by graphs, and then the wrenches are arranged in the unit action matrix, which is a matrix containing all those screws that represent forces. Here we have this representation, the steps the seed mechanism, the coupling graph, the cut set graph, and then the action graph. Now, the redundant constraints can be calculated using this equation. Q is equal to C. C represents the independent constraints, and the rank of this matrix is the matrix of ranges representing forces, and then the rank is calculated to compute the number of independent columns of this matrix. The mobility of mechanisms can be calculated using this equation. This is the mobility equation, but these terms are added, so we are considering now the independent constraints and these redundant constraints. Consider, for example, this Baranov chain that contains 5 links. In the planar screw system, this kinematic chain has mobility equals to 0, m equals 0, and the lambda is 3. It's a planar system, it's the planar workspace. The number of links is 5, and the redundant constraints are 0, because in this case, each joint is represented as a revolute joint. The number of independent constraints is 12, because for each joint, there are two independent constraints. If every joint of this Baranov chain is a revolute joint, revolute joints have 2 constraints in the planar screw system, and the kinematic chain has 6 joints. So we have a total of 12 independent constraints. Then I introduce this concept of Assur virtual joints. Because joints have 3 constraints in the planar screw system, the kinematic chain has 6 joints. We have a total of 18 independent constraints, and there are 6 redundant constraints. We need to remove these constraints in order to construct mechanisms that contain no redundant constraint. This concept of Assur virtual joints was used to define these joints that have not already been defined, but Barreto actually changed this concept to Rechet of joints, because it is more connected to the idea of defining the type of the joints. By removing constraints from an Assur virtual joint, every other type of joint can be created. For example, if we remove this constraint here, a revolute joint is obtained in the z-axis. I mean, if we remove a constraint, I will explain this better, but if we remove, depending, if we have a revolute joint in the plane and then remove from this the constraint of the movement in the y-axis, we obtain a joint with movement. It will be clear if I represent this, if I introduce this concept with an example. So using the Davis method for the Baranov chain made with an Assur virtual joints, then this is the action unit matrix for this kinematic chain. There are a lot of redundant constraints, and these redundant constraints are needed to be removed from this chain in order to obtain a mechanism with the joints, the type of the joints defined, and without redundant constraints. In this example, we have obtained this mechanism removing some constraints, and this second mechanism where the joints are defined. However, this remotion of constraints cannot be random, because in some cases, a mechanism with linear dependence can be obtained. A Baranov chain has mobility 0. In this case, this mechanism has mobility 1 because there is a linear dependence between the freedoms of these 2 joints, and it acquires degrees of freedom. Now, the method presented in the paper, which is the development of new gripper mechanisms. A gripper is a mechanical system designed to grasp and release objects. When grasping an object, the mobility is 0. if the contact is, if we assume the contact between the object and the finger as a point contact with friction. So we consider the contact as revolute joints. It's the same concept used in the previous paper. The seed kinematic chain for this example is this 9-link Baranov chain, which contains M equal to 0, J equal to 12, and N equal to 9, the number of links. Lambda is equal to 3. Using Davis method, the network action unit matrix has rank R equals to 24 and C equals 36. We must remove 12 constraints to create a new gripper mechanism. This is the table representing what are the joints, which joints have been removed in order to obtain this mechanism. For example, we have joint A, and the constraint removed is U. U here represents a force in the x-axis. So if we remove this constraint, the joint obtained is a joint with linear motion in the x-axis. Another example, the joint G. The constraint removed is a force in the y-axis. If a force in the y-axis is removed, the joint obtained is this revolute joint. Am I right? Okay, thank you. In the second example, this mechanism is obtained. Again, example, if we take as an example F, the constraint removed is U. U is a force in the x-axis, thus the joint F is obtained, which is a joint with linear motion in the x-axis. The process is the same for every joint, so we remove constraints and we define a mechanism with the type of the joints defined and without redundant constraints. This is the third example, and this is the fourth example. This is the conclusion. If the pros of this method are, it can generate new kinematic structures using the Reshetov virtual joints, actually the Assur virtual joints and the Davis method. By removing columns from the network action matrix, the process is easy and straightforward. The cons are, after each column is removed, the rank of the matrix must be checked because we don't want to obtain joints with linear dependencies, because the mobility is undesired. Generating multiple different mechanisms can be troublesome, so we can use matroids to automate this enumeration process, because in this example, we are making it one by one, joint by joint, and removing. But using matroid, we can have the unit action matrix, the action unit matrix, and then compute the matroid of this matrix, because the result is a set of linear independent columns which represent a mechanism without redundant constraints. Thank you. I have finished my presentation. If you have any doubt, feel free to ask me.
Thank you, Fernando. Any question? If there is no question, thank you again. Thank you. I know very well these words. So I have no question. Thank you, Fernando. We will continue with the group of Professor Jara Alegría. The next work is synthesis and sensitivity analysis of a prosthetic finger. Elvis is here, Del Piero,
Hi,
Arroyo
Martin.
Vera.
Yes, Del Piero will present the paper.
Yeah, I'm here. Okay, I'll share my screen first. Let me know if you can see.
Yes.
Okay. Well, let's start. Good afternoon to everyone. I'm Del Piero Flores. I'm studying mechatronics engineering at UTEC in Peru. Here's my email and the email of the rest of the authors. I'm going to present you the paper synthesis and sensitivity analysis of a prosthetic finger. Here you have the table of contents about this presentation, and then we have the motivation. Okay, in this paper, the Toronto mechanism is analyzed and synthesized using genetic algorithm to allow the finger to grab specific objects in a natural way. Additionally to this, we made a sensitivity analysis to discover which of the variables have significant causality in the end effector trajectory. These variables could be manipulated then to reach a desired trajectory as a reconfigurable version of this proposal. Okay, to talk more about the Toronto mechanism, which is the principal mechanism that we are using here, this is composed by 3 phalanges and also a slider crank and additional linkers. We have the proximal, the middle, distal phalanges, which is as the same as in a prosthetic finger, and then we have the linkers and the linear actuated slider crank. We could represent the mechanism of Toronto in 4 sub-mechanisms. We have a set of 3 linkers here, which is in green. Then we have 2 forwards, and finally our linear actuator, the slider crank. For forward analysis, or like kinetic or kinematic analysis, we need the parameters of this mechanism, the initial parameters here. And these are the principal parameters. We have the distances of the linkers and the specific angles, of some angles that are needed to describe the Toronto mechanism. Okay. Then we have the kinematic analysis, and for the kinematic analysis, we made the position analysis of this Toronto mechanism. It is determined using the following equation. As I mentioned, we have 4 sub-mechanisms here in the Toronto mechanism, which is the slider crank, the set of 3 linkers, and the 2 forwards. Where here 0 is a right of shape of 2, and E is the unit vector of its associated link. And finally, we have a vector of unknowns. And in this case, there are 8 unknowns, which are the angles and the distance D1 of the slider crank. Since this is a system of nonlinear equations, the unknowns can be calculated in a iteratively way using the Newton-Raphson method. So we consider a vector phi of shape of 8 by 1. And it contains the nonlinear equations 1 to 4 presented before. And we obtain the respective Jacobian here, which is the partial derivative of phi with respect to the unknowns. Okay, then we can calculate, making iteration, we can calculate the variations of the unknowns here as presented. Solving this using the method, the Newton-Raphson method, we can make the simulation here in a software, in this case MATLAB. The objective, as I mentioned before, is to determine the end effector position or the trajectory. And in this case, we need the position for each instant of the end effector, which is J12. Therefore, we only need this equation to get to this position. Here is presented, and we can see the simulation here in MATLAB. A half revolution of the slider crank implies the flexion of the finger to this point, and the other half will return the finger to the initial position. And this is the trajectory of the end effector. Then we have the kinetic analysis of the mechanism. For this kinetic analysis, we need the inertial properties, and those were determined using a CAD software. In this case, the Autodesk Inventor. And they are shown in table 2. We have the mass and the moment of inertia of those links. It is important to specify that we used plastic ABS as the material of the links. And then we made the free body diagrams, but in this case, we consider a perpendicular force of 1 Newton. This is important. Well, in this case, it is perpendicular to the J8 to J12 projection because it simulates the reaction caused by holding an object with a prosthetic finger. Here it is represented. We can represent the external force here that is actuated to J8 to J12. Then we apply the Newton's second law to all the links of the mechanism, and then we can obtain the required torque during the whole process. And we have figure 4b, and we can obtain the maximum torque that is applied. In this case, is around 0.1 Newton meters. And that will be about the kinetic analysis. Then we go with the sensitivity analysis. First, we have the context. As until now, we proposed a prosthetic finger, but this is fitted to a specific predefined trajectory. Then it may be a drawback when a human finger needs to follow different trajectories. For example, if we have a closing movement for different object sizes, as presented in this figure. Then we solve this adjusting some link dimensions to reconfigure the finger's trajectory. Okay, as we want different trajectories or simulate different trajectories, we present in this case 5 different paths here to simulate objects with different sizes. As we want to reach or we want to pass through a different path than before, we now have optimization problem. For this, we use genetic algorithms. Then after using optimization using genetic algorithms, using also the restrictions for this application, we have new parameters. Well, in this case, we have the initial parameters in this table and the new parameters for each path, path 1 to 5. Then, since we can optimize the mechanism, the parameters of the mechanism, the principal parameters, and we can have desired trajectories, there are some problems when we make the optimization, because there could be variations in the variables that could imply a non-anatomical shape. So we don't want a non-anatomical shape since it is anesthetically and it is not natural. So we want, in other cases, we will have an anatomical shape. From this, we have to analyze which of the variables varies the most, and also that doesn't imply that they don't imply in a non-anatomical shape. Okay, from this, we have from the genetic algorithms the percentual variation of each of the modified parameters. As we can see with a threshold of 10% of variation, these variables, 3 variables, which are the gamma 2, B1, and A4, are the variables that varies the most during the genetic algorithms here. They also, with the appropriate restrictions, they also doesn't affect or doesn't imply a non-anatomical shape in the finger. Okay, here are the parameters that I mentioned is B1, gamma 2, and A4. According to this, B1 and A4 are linear, they are distances. So we could have 2 linear actuators here to change these distances. Then for gamma 2, which is an angle, we could have a rotary actuator here. Then we have 2 linear actuators and 1 rotary actuator for changing these parameters. And to conclude, the synthesis and sensitivity analysis of the Toronto mechanism used in this prosthetic finger have been done. This simulate the flexion movement of a finger the complete movement. And based on our kinetic analysis, a slider crank mechanism is sufficed to generate the necessary linear movement and to drive this mechanism. Therefore, it's conveniently to propose this mechanism as a driver. And finally, the finger trajectory cannot be changed significantly due to the mechanism restrictions. As I mentioned, the non-anatomical shape that we don't want that shape. However, a reconfigurable version of the mechanism could be designed using tiny linear actuators for links B and A4, the distances that varies the most, and a rotary actuator such as a servo motor to change the angle gamma 2, which is the angle that varies the most. And this in order to have the capacity of picking things of different shapes and sizes in a comfortable way. But we have to add some degrees of freedom for this. Well, and that will be all. Here are the references, and thank you. If you have any question.
Thank you, Del Piero. I have some question. Do you can alguien levanta la mano? Juan Antonio. I will do a short question. You can use this procedure to design an exoskeleton of the finger?
Exoskeleton of the finger. Yeah, actually, that is true, because this project is also like pretending to further implementation with this mechanism, right? We have the linkers and we have our driver, that is the slider crank, and we could design an exoskeleton with that for this finger.
Okay. Yes, I met people in Idaho State University which was working on fingers, but from the fingers they take the idea to design exoskeleton for rehabilitation of people in coma. People in coma, using robotics, you can extend and contract the hands to awake the people who are in coma by several months. So it was nice to use the same procedure to design exoskeleton for rehabilitation. It's nice. Juan Carretero.
Thank you for the presentation. Maybe this may be a somewhat naive question. Can you, the first part of the question is, can you remind me how many design variables were you looking at as the entire, as a set?
Okay. Here.
Okay.
These variables. These are like the principal variables. There are other distances and angles, but these are like the principal.
Okay. So here, maybe keep that slide. So you have a number of these variables. I'm assuming you had bounds on all of them. So that is in your optimization, you didn't allow to vary these dimensions widely.
Yeah, for the genetic algorithms, we have the bounds, the restrictions from the upper limit and lower limits for these bounds.
Okay, so how did you, I guess, okay, so that is leading to my questions then. So one is, how did you decide on these bounds? And the most important one is, and again, it may be a naive question, but why did you decide to use a genetic algorithm that cannot give you an exact solution, unlike, say, a gradient-based method? Did you, are you certain that the problem is multimodal?
Okay. Well, the first reason how we design these bounds is because as the first thing that we made when we're making this research was just to maybe put some points in the graph here, for example, in the simulation, just adding some points, and maybe we want this to follow those new points. Yeah? And we arbitrarily change some parameters. Okay, we arbitrarily change some parameters to follow that points. Then, as we can see, there are some restrictions that we need because if there are like a huge variation, that could imply in a non-anatomical shape of this. Then we have like boundaries that are so close to the current values, but they allow us to change the trajectory. And about the way we use genetic algorithms, well, that was just about the research or how to apply genetic algorithms in this kind of research. Since we want to use an optimization problem, we have an optimization problem, and we just use genetic algorithms to solve that, taking account the boundaries because they don't have a lot of variation in this case, or they shouldn't have a lot of variation. And maybe another kind of problem solution or optimization problem or solution is they usually don't use these boundaries.
But one of the issues of GAs is that they do not use any sort of gradient information, and your variables are continuous, and your objective function is, you can also take the derivative of it. So you're not taking advantage of all that information that is available for you. And I do not, if I'm not mistaken, your objective function is a relatively simple algebraic equation, right? Computationally, it is not expensive.
Mm-hmm. Okay, yeah, it is. That would be maybe something that we didn't take advantage of that, and maybe it could imply a new research or to improve this design to make it more it maybe a better solution. But in this case, we just used those boundaries and genetic algorithms to obtain that.
Okay, thank you.
More participants.
Hi, Martin. I would like to say something as well. Actually, we used also a gradient-based method for optimization. And actually, we obtained it as a similar response on the mechanism as well. Then actually, we are not taking some advantage of using genetic algorithm yet, but actually both of them are solving our problem for now.
So if that is the case, I would say the GAs,
exactly.
You're not taking advantage of it. You're actually
exactly.
hurting yourself by using that as opposed to using a gradient-based method.
Exactly.
Much the opposite. Yeah.
Exactly.
All right. Thank you. Yeah. Thanks for answering.
Thank you very much, Elvis and Del Piero.
Okay, thank you.
If there is no more question, we acknowledge again. Thank you, Del Piero. The next presentation is also from the same group. Jean-Pierre Figueroa.
So I will share my. So tell me if you see.
Joseph Diaz is here also?
No, he couldn't.
You're alone.
Be,
okay.
Yeah.
No.
So I start, I think. So good afternoon, organizers, professors, and colleagues. Thank you for having me today. My name is Jean-Pierre Figueroa, and I'm going to present you today my team's research, synthesis of an exoskeleton and walking pattern, identification for a rehabilitation system. The team is composed by Joseph Diaz, Gustavo Quino, Elvis Legria, and who is talking to you, Jean-Pierre Figueroa. This research reacts to a global health problem in which millions of lives are suffered. According to the World Health Organization, more than 10 million of people need a wheelchair. all over the world. And here in Peru, more than 900,000 suffer from some motor impairment. Therefore, there are so many people in the global population that need mechanical or electromechanical support to mobilize them. And the problem worsens in developing countries in which it's too difficult to find a moderate treatment as ours. So one solution for the lower limb disability nowadays is the use of robotic systems as mechanisms to guide or generate the movement that the patient must follow. Some examples are rewalk, suit X, and hole. These exoskeletons have a high performance for treatment, but one thing in common with this alternative is that they have more than 1 degree of freedom to make the movement happen. Thus, they are so expensive and need an accurate control of their actuators. For that reason, we're interested in a low-cost portable rehabilitation system based on a 1 degree of freedom mechanism. So the patient can use it at home. Our rehabilitation system is based on a modified TVSM mechanism, as you can see, which is the portable and attachable to a conventional treadmill. Exogensen, which is the name by which we refer to the mechanism, can make 2 different rehabilitation exercises, walking and jogging, for 2 stages of the treatment of the patient. These walking patterns were obtained using a motion tracking algorithm for getting some representative points of each movement. Therefore, exogensen could be calibrated to minimize the error between those representative points and the initial ones. So we started doing the cinematic and kinetic analysis of the exogensen. A kinematic analysis is conducted to determine the position, velocity, and acceleration of the entire mechanism in function of the current kinematic state. Furthermore, the kinetic analysis is about determining the forces and torques acting on internal parts of the mechanism. Both analyses give us an idea of the mechanism behavior in torque and movement terms. To analyze the exogensen kinematic, we divide the exogensen into 3 simple forward linkages defined by the points A, B, C, D, A, B, G, D, D, H, F, A. Each group of the points for a loop. So there is 3 loops in the linkage, in the whole linkage. Every link has a particular angle. Consequently, each loop is characterized by a vector equation with which we achieve the visualized kinematic equations. The kinetic analysis process is based on a free body diagram corresponding to each element of the exogensen. The analysis is performed using Newton's laws applied to arrayed bodies that obtaining the kinetic equations shown. The effect of gravity is taken into account, and the mechanical properties of the elements to be analyzed, such as mass moment of inertia, and coordinates of the center of mass, were obtained through the chosen material, which is aluminum with 20 millimeters of width. Eventually, after the analysis made, we get the minimum torque required for the movement of the current for a complete cycle of the motion, which presents a sinusoidal behavior that evidences the smooth movement of the system. Also, we get the trajectory of the end effector P, which shows us that the computational synthesis for the mechanism is needed for our purpose. Hence, what we do in the computational process is an optimization of the link lengths, considering each rehab trajectory as restrictions that the new mechanism must accomplish. The physical movement of both rehab trajectories, walking and jogging, are sampled using a motion tracking algorithm. The walking and jogging sequences are recorded using a treadmill. 2 points marked with a fluorescent color are located on the knee and ankle. These points are filtered using a thresholding process so that the only trajectories of the ankle and knee are sampled. After the sampling trajectories, we need a scaling process. For this, it is necessary to consider the femoral head zone as the system of reference. Then some representative points are extracted. These are, for example, the initial position, the extremes in the x-axis, the peak in the y-axis, And in the case of knee, just extremes are considered because the over-restriction and the mechanism synthesis process. Eventually, we define a cost function with the norm between the actual points and the desired points. Also in the cost function, we are weighting the relevance of the representative points. As you can see, lambda is our parameter for this weight constant. In the show figure, we see a non-optimized exogensin and its uncle and knee trajectory. The optimization process starts with this mechanism's length, and then the algorithm will look for a better configuration than that accomplishes the desired path. However, this is more than one configuration. There is more than one configuration that can optimize the function cost. Therefore, it is necessary to impose some length boundaries. The restriction for the optimization were collected experimentally from people with height around the proposed mechanism, which is 1.6 meter, because we want a more anatomic behavior. This table represents the obtained restriction links. Links 8 and D are fixed in their actual lengths. Meanwhile, the other links have a range of optimization because they are regulable. As a result of the optimization, the initial cost has been reduced by almost 90% for walking exercise. Also, the optimized links are among the imposed range of optimization too. Also, the initial cost of jogging exercise has been reduced by 93%. The optimized links are among the imposed range of optimization. So as we can see, the mechanism was optimized for both rehabilitation exercises. The final cost is lower than the initial one because the achieved trajectories pass through the characteristic points. On the other hand, the position of the of a range made the adjustments not vary so much. Finally, knowing there is a sampling time for the simulation, as we can see, the distance between the points happen at the same time. Because the velocity of the current is constant. So in the areas where the points are further apart, there is a higher velocity than the areas where the points are close to each other. So this can give us an idea of the behavior, and this corresponds to a real movement of a patient. This research is based on a defined patient with a defined height. However, if we want to use optimized exogensin in a different patient with a height different, very different to the actual one, it will not be adapted to his body. Thus, what we're working on is an adaptable mechanism that, depending on the parameter, can change its dimension. This parameter will be related to the patient's height. On the other hand, we want the mechanism to have just a specific regular links, so the rest can be fixed. So in brief, the principal conclusions are these. The minimum torque and diameter motor was defined through the kinematic and kinetic analysis. For the synthesis process, movement patterns were required. Then we collect data experimentally for the reference points. Weight cost function was proposed also to impose that some reference points are more important than the other, so that an anatomical movement is reached. The mechanism was optimized for both rehabilitation exercise, decreasing the initial cost of 89.8% for walking and 83.6% for jogging. The optimization of point F was essentially, point F is the knee. So because our anatomical purpose for a great patient comfort, because there will be an over compression and extension of some human body's parts on the leg. So with our main future work is the adaptability of the exogensin for the users of different sizes by adding just a constant proportionality parameter. So here are some reference, and thank you everyone for listening, and I hope you enjoy my presentation. If anybody has a question, I'm open to answer them.
Thank you, Jean-Pierre. Question by Juan Carretero.
Thank you. Hopefully I'm not too annoying with all my questions, so I'll be relatively quick this time around.
No, it's a pleasure. Thank you, Juan.
Yeah. So based on the last, if you can put the last slide, I think in your conclusions you had two numbers there. I just want to be able to, yeah. Oh, you just passed it there. We iteratively get to it. Perfect. So you used a metric to define how close you are to a specific trajectory, which is essentially based on your initial guess. Is that correct?
Yeah, that is here.
How good was, yeah, how good was the original guess? Because I could have started with a very, very poor guess, and then I could have shown that my optimization was 99.9% good, but that remaining 0.1% may still be very far from an ideal trajectory.
So yeah, the first one, the initial link length, it's the meter, the initial value. So that were obtained using a paper. So we get these distances of the lengths. So there were in the thesis there were optimized for just make this movement happens, not for an specific points. And what we use them, and what we would like to make with these points were to pass for some representative points of different exercises for walking and jogging, and as mentioned. So they were not so bad. They made the thing that is how the knee and the point, the end effector has a trajectory, and that's the answer.
Okay, sorry. So if I get it correctly, you got it from some source, from a paper that had already been published. These dimensions, were those dimensions in that paper that you're referring to, were the dimensions already optimized?
Yeah, for a single purpose. There were no the same purpose as ours. They were just were looking for using the Theo-Jensen mechanism modify to just make this trajectory, the initial trajectory. But they were not looking for a walking and jogging trajectory.
Okay, I think I understand it. Okay, thank you. That's all.
Any other question? No. Are you considering velocities, Jean-Pierre, or the correspondence between point and time?
Yeah. Teacher.
Elvis?
Yes, Martin. Each point is related with a position of the crank. Then we are assuming that the crank is rotating with a constant velocity. Then each point is reference point, yes, is associated with an instant time. Then we are considering velocity as well.
Okay.
Yeah.
So the crank is constant velocity.
Exactly.
But the velocity of the trajectory on the foot and the leg.
Yeah, on the knee and on the effector. Okay. On the ankle as well.
But they are correct velocity for the ergonomical motion or biomechanical. They have sense. This velocity when you impose a constant velocity crank.
Yeah, we need to improve that as well. We are proposing a rigid mechanism, but we know that actually the knee and the ankle are not fixed point that we need to have some tolerance of movement there in order to avoid some overextension, for example, of the links. I don't know if that was the question.
No, the question is the correspondence between the trajectories, if they are biomechanical correct for a person who walk.
Yeah, we did 2 experiments, one for walking and another for jogging. And in each case, we obtained a reference associated with their velocities. Then we expect that both are okay in both cases.
So you are satisfying the points on for each time captured by the motion.
Exactly. Yeah.
Okay.
Yeah.
Juan, you have another question.
Well, it was a follow-up of your question, Martin, because it seems to me that is a quasi, at least the way it was presented here, it seems to be a quasi-static study. But I agree the velocity would be essential, and any deviation from the upper point that you guys called it point F and the one underneath, it will have a variation in terms of distance between the points, as Elvis just pointed out, right?
Exactly.
So it's velocity and relative distance is important, especially if you're going to attach this to a human.
Exactly. Yeah, that is an important thing that we don't talk about in this research, but we need to have some flexibility on the point where we attach this exoskeleton to the human.
But that means if you have the flexibility as you're talking about, then your trajectories as designed are no longer accurate.
Exactly. We are assuming that everything is exact. We are assuming that everything is a rigid body in this linkage. But we need to maybe later design something to attach some flexible attachment device, device to attach this joint to the human.
Okay.
So I want to add some ideas that for walking exercise we get 40 revolutions per minute of the constant crank. So that is less than 1 revolution per second. So I think this is an anatomical movement. So there is not an hyperextension and compression in a minimum time. So there is, I guess, a more anatomical thing.
Okay, thank you. Thank you very much. If there is no any other question.
I would like to add a short point,
Elvis.
Martin, about the question of Juan Antonio. That was a good question about how did we choose the initial values. It's because actually the Theo-Jensen linkage is a known linkage, isn't it? All the linkages are quite defined, but it is not defined for a human walking necessarily.
Yeah, yes, for art.
Exactly.
Animal art. Yes.
Exactly. Yeah, and then we need to adapt this linkage for another one that could be similar to a human movement. In this case, we propose to move one point of this link. For example, the point G in the original linkage is not placed there. It's placed in H, I guess, in the H point. Then they move this linkage. For that the reason we said it is a modified Jensen linkage. And these initial values are based on that nominal exo-Jensen, the Theo-Jensen linkage. That we choose those values as an initial values for our optimization process.
Yeah, then you adjusted the bounds experimentally. Yeah. For instance, the value A is fixed because the lower bound and upper bound are the same, the A and D.
Exactly.
Can you show the table, Jean-Pierre?
Yeah.
The table before that, A and D. The lower boundary, upper boundary are the initial value. So they are fixed value. Their parameters are not are not variables.
Exactly. Yeah, those
So
are fixed.
you are given a human trying to obtain human motion with Theo Jansen.
Exactly.
Is this
Yeah.
the first work and I do that, or have you seen that in another journal?
Yeah. How did you inspire on that proposal, Jean-Pierre? On moving that
Of the Theo Jansen?
Yeah, on
Yeah.
changing the
Yes, I
configuration, the
saw
initial configuration.
all the videos on Theo Jansen, but it's very original to try to use for human. It's very nice to see.
Yeah, yeah.
So keep going and doing research on that. Yes, I hope you will success, because the machine and the beast and animal works very well.
Yeah, that's true. That's true.
Okay. If there is no more question, we will close the block of the dimensional synthesis. And we give the applause to Elvis and Jean-Pierre. Thank you very much.
Thank you.
So,
thanks.
We will deliver about the next block. Now there will be a break, but there are some suspended presentation. So after the break, next presentation will be Carlos Rodriguez at 3:30, 15:30. Carlos was here, is here. Okay. So instead of doing a break, we can hear your presentation, Carlos, because we are very near from the time. And Luan Vinicius Arman and Luan Meneghini have canceled the presentation. Paulo Rossi is here. Andrea Piga, his director, tell me that he will present it. No?
Professor, Paul is not here, but he will present his work.
Fernando?
Yes, and
you
Paulo,
will present it?
No, but Paulo will present his work. I have talked to him earlier, and he said that he had his presentation ready.
Okay, and when he will join us, because Carlos will finish 15:45. Maybe we can assign a plenary
I believe
time.
you can contact him
Carlos.
to do it earlier.
Okay,
I will try.
so we have two presentations next. Carlos Rodriguez and Paulo Rossi. So Carlos, you have a lot of time. If you can use more time, you're welcome. It's like a plenary time for you, if the attendant agree.
It's okay, I can use the time everybody's using.
Okay, thank you, Carlos.
Right.
Let me introduce you, Carlos Rodriguez.
Thank you. Can you see my screen now?
Yes.
Cool.
Present the study of a class of variable geometry truss manipulator.
All right, so I'm going to present this as a work of one of my students, is Santiago Iregui. He was my former student in the master's degree program that we have in Los Andes University in Bogota, Colombia. But he's currently doing his PhD in Leuven, Belgium, so he cannot join us today. And it's about this new class that we are proposing of variable geometry truss manipulators. The motivation is as follows. We have, let's say, two general main families of manipulators, the serial ones and the parallel ones, structures. But we would like to have those characteristics that are especially the limbs with lower inertia, and the ratio load to weight. That is very, very attractive. So in the state of the art, we have some previous ideas. One are called variable geometry trusses, and they correspond to, let's say, a truss with some of the links that are actuated. They are used especially for shape correction when the structures are under load. And on the other hand, we have also adaptive structures that they're mainly used as you see for morphing the shape of the wings in aircrafts. So from these ideas, we propose this to extend the truss, the variable geometry truss manipulator, let's say, for one that is fully actuated. It means that every member is an actuator, an extensible or translation actuator in this case. The configuration is as follows, or the definition is as follows. The configuration is like a truss. So we form triangular closed loop kinematic chains, and each edge of the triangle is a linear actuator. All edges attached to a given node have a common axis, and finally it is statically determinate, so it implies that it has only two joints with the earth, let's say. One is a pin joint and the other one is a roller one. Here we have some examples that we can construct using this definition. And in the lower part, there are some that are not part of this class because they don't obey one of these rules that I already commented. So here are some examples of motion that we can perform with this type of manipulators, but I will explain those in further detail later. The main idea of having these manipulators, the definition I have previously stated, is that we can have a graph representation of them. So taking these two examples, this we can use the triangles as nodes and the arcs as the vicinity among the triangles. So there is like a dual representation between these manipulators that we defined and a connected graph. This characteristic is very useful to define them in a systematic way. So we develop a toolbox to define them, and we can just construct them easily, adding triangles and defining the vicinity among them. At the end, we have to just to define how they are attached to the ground. We studied some of the classic, let's say, methods for the manipulators. We studied first the power kinematics, and using the dual representation as graphs, we can use the very well-known algorithm is called Dept first search that allows us to define a systematic way to have the power kinematics of the manipulator. So given the extensions of the links, we started using this Dept first algorithm in order to solve all the vicinities. And at the end, we just solve the ground location of indeed, ground angle of this member that solves the forward kinematics of the whole manipulator. As usual, when you have this redundant manipulators, we have singularities. So we studied also them, and we encountered three types of those singularities. One is when two of these points come together, so there are no extension of one of the sides of the triangle. The second one is when when one of the triangles squeezes in the way that two of their sides equal the sum of two of them, or the size equals the third one. And then the last one is when two points of the different triangles go to the same point, especially those attached to the ground. We saw that these singularities are mathematically feasible, but when you construct a prototype, it is usually good you have a minimum extension of each of these sides, so they are practically impossible to achieve. So it's very interesting that these singularities are not present in the real manipulators of this class. Then we go through the statics. That's because their similarity with the trusses. It is well known that you can just, if you have external forces applied on a truss, you can derive a matrix that is let's say, like kind of rigidity matrix that relates the external forces with the internal forces of the elements. In this case, the external forces are F and the internal forces are tau. Tau will be the forces of the actuators in our case. So the matrix that we call here D, it is simply computed using the unitary vectors of the links of the manipulator. And then we can, having the external forces, we can easily, inverting the matrix D, having the internal forces in the members tau that correspond, as I said, with the forces in the actuators. Using the duality between the velocity and the force, and especially like for those static or kinetostatic indexes, we can just use the above definition to explore the inverse kinematics. The inverse kinematics, in this case, as always, we need the function that relates the internal or the actuator joints, the actuator variables, through the external desired position or pose in general. So we started with the definition of the Jacobian matrix, and we stated, or used the duality among this definition and the definition of the torques, using that the power is conserved. So we identified that this matrix, the transpose of the Jacobian, is exactly the inverse of the above defined matrix D. So we use it in order to develop a classic inverse kinematics algorithm. Before we have to select which of the points will be the one of the we are interested to position in given positions of the workspace. So we select those points, reducing the Jacobian matrix. So this matrix that could be a square one, in general, the reduced Jacobian matrix it is not anymore a square metric. So we have to use the Moore-Penrose inverse in order to solve the equation properly. But this allows us, is more or less usual, to have the solution divided in two sets. One is the minimum non-velocity that gives the, let's say, the external final position of the end effector, and this that projects into the nullity of the space of this Jacobian, reduced Jacobian, that is very interesting in order to optimize some of the behaviors of these manipulators. We use this algorithm, and we constructed this prototype with electrical actuators in order to perform different paths, like not very simple paths, like circles, for example, different diameters. But we have also here a shape like an infinite, similar to the infinite. And here we have one of the, I guess, most interesting properties of this manipulator is that you can control two of the nodes as outputs. So, for example, commanding one to move around one circle and the other one moving around a different circle. Of course, with a simple algebra, I have to say, you can also imagine that you have like a end effector here, and you can control it in position and also in orientation, at least in a plane. We also studied the idea of having bistable actuators, understood as actuators that only has motion between their extremes, the two final positions, like, for example, those pneumatic actuators. And we collected, here we have, let's say, the collection of points that are reachable, but this node in particular, this node selected as the node of interest, is called the node number 6 in this case, but it is irrelevant. And we just depicted here half of because obviously this manipulator is symmetric, so we have half of the points that are reachable, and you can see that the motion is very interesting, and we have like let's say a workspace that it is reachable just using two positions for each of the actuator, in this case edge of the triangle. And here is one example, and in the right we have a different example with another manipulator of the class. So the reachable space is good enough. I guess that our opinion is that it could be also very interesting to have like these bistable actuators. And here we have a different show of with other manipulator, the same kind of trajectories, the circle, the infinity, but here we have, let's say, like a straight line, is something that is very useful for many applications. Here, because of the richest space, it is just performing one in here, but also as it is a very redundant manipulator, it has the capability of surround or avoid some certain obstacles in the workspace, as I'm showing here in this video. So as a conclusion, we have proposed this new class of hybrid hyper-redundant manipulators. The name is not too easy. It's a variable geometry, fully actuated truss type fully actuated manipulator. And we studied some of their properties. Due to we use the truss topology in order to define this graph formalization that allows us to propose methods for computing the forward and inverse kinematics, and also we studied the singularities. And finally, we think that this redundancy, this redundancy made the robots very attractive, very versatile for handling different situations, since more than one node can be simultaneously controlled. Well, this is the presentation of the work of Santiago, and was advised by me, and I will be glad to receive questions as you have.
Nice. Thank you, Carlos. Nice presentation. Some question for Carlos? No, nobody raised the hand. I have a question. Which is the next direction? You will continue with symmetrical triangles?
Yeah, well,
okay.
it don't have to be symmetrical. We're using that symmetrical because it's usual to have to say the same actuators for every every side. But we also have an additional work. I'm trying to show it here. Let me see if it works properly. It is how to use the redundancy as the optimization of force. Here we have let's suppose that this blue thing is an external applied force, and we move the manipulator through different positions of this node, and then the configuration that arises is the one that minimizes the internal forces of the elements in some sense. So it is a nice future direction for this kind of manipulators, is to simultaneously control the force optimization and the trajectory of some of the nodes, some of the interesting points of the end points. And this particular prototype is very, let's say, lab testing bed, and we have some issues with the rigidity in the plane, out of the plane. Yeah, this is vertical now. Now it is vertical, but we have some issues because it is like a plane, so it is not, let's say, structurally rigid enough to perform like an external real force. Let's say this will be also a nice direction. Future direction is how to use them or extend this definition to a three-dimensional space.
In three-dimensional space, the unit will be a tetrahedral?
Yeah, for sure, it will be.
You cannot
also
do two elements only. with that one. With that
yeah. Yeah, because we have few of these actuators right now.
Okay. You have nine actuators. Okay, any other question? Interesting work, Carlos.
Okay, thank you very much for your attention, for your questions.
Thank you, Carlos Rodriguez again. And now we are waiting for a presentation. Some presentation was canceled. Luana Menghini is not presenting. Paulo Rossi is here.
Yes, I'm here.
Okay. Paulo coming. Andrea Piga, tell me that you were here. So you can start before the schedule and take more time if you want it. We have a missing question for Carlos while you present. Juan Carretero ask if the design is modular.
Yeah, just if your design of the actuators and the trusses, are they modular at this point?
Yes, they are. We don't design the actuators, we just buy them.
Okay,
this
and
is like
what is the range of motion?
It's very short. They are like 14 centimeters, and they're long, and the range is like 6 centimeters. They are very popular in there from Canada manufacturer, Canadian manufacturer.
It is 13 when they're compressed and 20 when they're extended. Is that what you just said?
Yeah, that's it. 14 to 20.
Okay, 14 to 20. Okay, thank you.
All right.
Interesting work.
Thank you.
Thank you, Carlos. So, Pablo is ready?
Yes, I'm ready.
Okay. Share your screen when you want it.
Okay, let me see. Do you all see my screen?
Yes, perfectly.
Okay. So, hello everyone. Today I'm glad to present to you my paper developed with my professors, Professor Roberto Simoni, Andrea Piga Carboni, and Henrique Simas. And the paper's title is Meta-analysis of a 3T1R through the coupled parallel manipulators family. So this paper proposed the development of the meta-analysis of the 4DOF 3T1R full decoupled parallel manipulator, which is known here as the coupled manipulator or the coupled architecture. And this analysis takes into account the position nematics, differential nematics, singularity poles, and workspace analysis. And the analysis first describes the robot's position in differential nematics, and furthermore, with the obtained data, the singularity analysis and workspace one can be developed in a theoretical manner. So the parallel manipulators are a sort of machine that have their base connected towards the moving platform through several nematic chains, at least 2 of them, resulting in multi-loop architectures. And several of these machines have 6 degrees of freedom. But, and here we have an image representing a parallel manipulator, a sort of Goff spheric platform, where the fixed base is connected towards the moving platform. And these kinds of machines have some advantages like higher stiffness, better dynamic performances, and reduced inertial mass. But for some tasks, the 6DOF parallel manipulators are cumbersome, and then the 4DOF or Schonflies motion parallel manipulators, for example, are broadly exploited machines in pick-and-place tasks, for example. And these machines, the 4DOF Schonflies motion parallel manipulators, have the same advantages when compared to the 6DOF ones, but summed with the simpler kinematics, usually. And here we have a GIF representing the H4 parallel manipulator in its prime. So the decoupled architecture, as I said, it was synthesized by Gyogu in his work here. And this analyzer parallel manipulator belongs to a family of parallel manipulators that consists of 10 topologies in a total. And this machine, this architecture represents such a family without losing generality. So the analyzed architecture graph representation is illustrated here, and the functional one here. One can perceive that there are only prismatic joints except for the last joints that are revolute type. And the Schoenflies motion, in which there are free translations along the oriented Cartesian axis, jointly with one rotational motion along with the x-axis in that case. And here is illustrated the CAD model, the developed CAD model for this work in order to analyze the kinematics. So continuing with the kinematic analysis and the manipulators, the analyzed manipulator characteristics, one can perceive that there are 3 prismatic joints, all orthogonal each other, and a last revolute joint in which is also orthogonal considering the previous prismatic joints, except for the second leg here, the head leg, in which the last revolute joint is parallel compared to the second prismatic joint. And the analyzed architecture also has decoupled motions, and it has Schoenflies or free T1R motion. So in the kinematic analysis, the position kinematic analysis investigates the displacement relationship between the actuator's inputs in the joint space and the end effector output in the operational space. And usually in the parallel manipulators, the position kinematics is achieved through the inverse kinematics, because usually they have cumbersome kinematics. Nevertheless, in some case, it can be simple to proceed with the direct kinematics instead, especially considering the full decoupled parallel manipulators like the studied one, like the decoupled architecture. And in the direct kinematics, we have the actuator's inputs here that are known, and through the actuator's inputs magnitude, one can achieve the end effector outputs. So in order to analyze the direct kinematics, let's consider the decoupled architecture CAD representation as exposed here. And taking the first leg here as an example and simplifying in a structural representation, putting in the XZ plane perspective, it is possible to note that since the P1A point is located on the fixed link, then it has fixed coordinates. So P1A point has these coordinates along X, Y, and Z axis that are fixed. And furthermore, the P1B point coordinates depend on the P1A points and also in the input link Q1 displacement in a positive input, leading to a negative displacement regarding the fixed reference frame. And the same rationale can be applied in the second and third legs too. But in this case, putting the leg structure representation in the YZ plane instead the XZ plane one, and considering either positive and negative displacements depending on the actuator's direction. Joining the three obtained equations for the first, second, and third legs respectively will result in the direct kinematic position equations as illustrated here for the moving platform. But however, the moving platform orientation has not been analyzed yet. So taking into account the fourth leg here, the same rationale used for the other legs can be applied here too, resulting in these equations. Moreover, considering only the moving platform represented here, in which the L2 parameter is its length along the y-axis, and it is known. Also, the L3 parameter can be represented as exposed here. Finally, calculating the sine of phi angle using trigonometric relationships and substituting the respective values will result in the direct kinematic orientation equation here. So at this point, we have the position and orientation, so resulting in the position kinematics equations. In the differential kinematics, the velocity analysis can be achieved through the Jacobian matrix calculation. And this matrix in parallel manipulator can be achieved through the position kinematics equations differentiation. So here we have the inverse and direct Jacobian matrix multiplied by the secondary and primary variables respectively. Then, considering the direct kinematics achieved equations and putting them together as illustrated here, and differentiating this set of equations with respect to time, will result in this set of equations in which there are velocities and angular velocity regarding the moving platform's outputs and actuator inputs. Furthermore, taking the previous equation respecting the direct and inverse Jacobians and substituting the equivalent values will result in the differential kinematics equations, as illustrated here. So the kinematic singularities of the Jacobian matrix can be calculated through the matrix determinant, that is, when the determinant is nu, there is a singularity pose. Since the inverse Jacobian matrix never has its determinant has nu, then there are no inverse singularity poses. Now, concerning the direct Jacobian, it is possible to perceive that there are singularities when L2 cosine phi is equal to 0. Therefore, one can conclude that these singularities will occur when the moving platform reach either 90 degrees or minus 90 degrees regarding the x Cartesian axis, of course. So continuing with the workspace analysis, it was possible to deduce that the workspace balloon has a parallelepiped shape through the developed CAD model displacements, as well the obtained position kinematic equations. Considering the first actuator displacement, there is a line. Jointly with the second one, there is an area, and considering all of them, there is a cubic balloon. And since the workspace is not cumbersome, it is also possible to calculate it mathematically. Taking into account the two possible situations for the moving platform orientation here, when the phi angle is positive or negative, it is clear that there is the necessity for a dimensional discrepancy between the input links to maintain a moving platform's specific position, let's say in this manner. This dimensional discrepancy is represented as dy and dz here, delta z in that case. And it occurs when, along with this axis, only along with the Z and Y axis. Thus, properly calculating the total displacement along with the Y and Z axis, considering these trigonometric relationships, will result in this equation, which can compute the workspace volume. The achieved workspace volumes for both CAD model simulation and the exposed analytical equation is illustrated here. These parameters were adopted, and these are generic parameters. So this paper presented the kinematic analysis of a representative coupled parallel manipulator proposed by Gowu. I mean, decoupled parallel manipulator, sorry. And position kinematics, velocities, singularities, and workspace have been studied. The direct kinematic analysis shows there is a one-to-one relationship between the input actuator links and the end effector position. The velocity analysis also produced a triangular smooth Jacobian matrix, enabling an effortless velocities map. The singularity posts are well conditioned, in which they exist only at convenient positions along with the workspace, namely the 90 degrees or minus 90 degrees. And both reachable and dexterous workspace volumes have a parallelepiped shape that was illustrated using generic design parameters. So that's it. Thank you for everyone. For the questions or comments, my email has exposed here.
Thank you, Paulo. Nice, very complete presentation. Any question for Paulo? Juan Carretero.
Yeah, a very simple question. So in your, if you show again your Jacobian matrix, that shows that is almost an identity matrix except for JP.
Okay.
Okay, so this it may be a question of semantics here, but you even in your title you said it is a fully decoupled manipulator. Yeah. And I think it's mostly decoupled in that that last row actually has a coupling between the third and fourth rows for the orientation. So position is fully decoupled from orientation, but I guess you can see that orientation isn't completely decoupled from position because it bears some term in the fourth row is in common with the third row.
Yes, thank you for the statement, and you are right. In fact, it is a decoupled manipulator because there is a relationship between the 30 and 40 rows. And in the most case, this analyzed architecture has decoupled motions. I mean, if we give end velocity to one actuator, then the moving platform will have the same velocity along with the same Cartesian axis, but in some case, it can be two, it can depend on two actuators instead of one. So yes, you are right.
Just as a follow-up, I've seen, while you were talking, I tried to find the reference, but I couldn't find it. But I know that there is a manipulator currently being proposed by some fellows at École Polytechnique in Montreal, Leonard Berglen and his team, that if I'm not mistaken is very close to this. now what they are using is the quadripteron topology. So it's not exactly the same, but I think it is. They are using essentially the kinematic constraints are the same. You're using P joints, passive P joints. What they're doing is they're using passive R joints, but then each kinematic chain is only allowed to move in, say, X, Y, or Z. So it's essentially, it's kinematically equivalent to what you have proposed, and it also has 4 degrees of freedom. So it also has Strumpfless motion.
Okay.
So the only difference being is that you have 3 prismatic joints mutually perpendicular to one another, one that is driven and the other ones that are not. So the 2 that are passive are constraining the motion to a plane. So what they've done is done exactly the same, but the constrained motion is happening with an parallel R kinematic structure, like the tripteron.
Okay. Yeah, in fact, this specific analyzer architecture was took from the Google work, but I'm pretty sure there are similar architectures proposed by other authors.
It's just, again, it's just compare your architecture to the tripteron. The constraints that you're putting on the 2 passive prismatic joints is essentially the same as what those fellows are doing with the tripteron. It's clever to also use prismatic joints, but it's kinematically, I think it is equivalent.
Martin, may I ask a question?
I have no more question, Paulo.
Yes, I would have a question. I would have a question.
Who is talking?
Manfred.
Manfred.
Oh, Manfred. Please go on.
Okay.
I can see. Couldn't see the hand.
Okay. Okay. I do not want to be very critical, but you told a lot about the forward kinematics and didn't tell us anything about the number of solutions you have for the forward kinematics. Did you do the forward kinematics, or are you just talking about it?
Yeah, in fact, the forward kinematics of this analyzer architecture is very straightforward, and it is simple. You mean the forward kinematics means the direct kinematics, of course, and yes, it did. I did it in this manner, in this simple geometrical manner as exposed here, in which one can perceive that if one input is given, for example, in the first leg has represented here, so the P1B point will move according to this input link magnitude displacement, and the action point is represented here as the red dot, and it is easy to see that this point will move according, I mean, in the same magnitude considering the input link magnitude displacement.
Yeah, but the solution could also be down.
Yeah.
You have the prismatic joint at the point P1B, yeah, allows you to go up or allows you to go down.
Yeah, actually, this prismatic joint is not actuated. So,
of course, it's not actuated, but it can move up and down. So you should have a second solution of the direct kinematics. The direct kinematics of a parallel manipulator is very seldomly unique. So in general, you would have more than one solution.
Yes. In fact, it can be studied to the other direct kinetic solutions, or even the operational the the operational space of the analyzed architecture, but here only this one direct embed solution is done.
Okay. Okay. So you're using one which is obvious for you, but yeah. I tell you, when you have a forward kinematic singularity, this generally separates two solutions of the forward kinematics, at least two. Otherwise you would not have a singularity. So you should do it carefully mathematically, and then you will get maybe a second, a third, or fourth solution. I do not know. It was a question. Yeah. The one which you show is obvious. Yes, that's correct. But there might be another one. Especially when you tell us that this matrix of the forward kinematic singularity can become zero. So this tells me that two solutions of the forward kinematics merge. This is usually the case. I'm sure Juan will agree with me.
Yes. Thank you. And it can be done in future works. But in this work, I have adopted these design parameters here, limiting the moving platform orientation between the minus 45 degrees and 45 degrees. So I intend to maintain the moving platform in a non-singularity pose, Digsters, and achievable workspace.
Yeah, may I ask another small question? It was not clear to me. How is the size of the workspace you were showing us, which is the translational workspace, dependent on the rotation of the platform?
Yes.
So it is dependent. It is dependent, yeah, for sure.
Okay. In this table, it is possible to observe that varying the moving platform orientation, the phi angle, also the total translation along with the y-axis and the z-axis too, it also varies, and the workspace volume too.
Okay, I didn't see that. I didn't see that. You didn't explain it. Okay, yes, I agree with that.
Okay, sorry for that. It's because a shortage of time.
Sorry, yeah.
I have just a comment. I didn't, it's my colleagues that did this work. I did not know about it, but just a short comment is that it was quite interesting to me to see Manfred, Arwin, Paulo. Paulo is a junior master student, and Manfred, I have seen Manfred destroying older senior guys with questions, and I was and I have to say that Paulo, you did very well for the time being. It's like a clash of generations.
Very well. It was just the question. I am not destroying him.
I know. We know, but just because I believe Paulo didn't know you before. Okay. So it's and maybe for this reason he was brave enough to keep up. Okay. No, just a comment, just a silly comment.
Yeah, that's true, Professor Daniel. And this was my first published paper, actually. And this is a simple and straightforward analysis of the couplet architecture.
So no more comments. One more hand, Daniel. There is no other. Thank you, everybody. So the last choice will now be given. This was the last choice. So we can acknowledge to Paulo again. Bravo, Paulo. Thank you for the question, Juan and Manfred. Sorry, Manfred, I put the participant list on your face there so you can see it. Sorry for that. Thank you for being here. Thank you, everybody. The program for tomorrow is actually the same, unless something canceled, but it is the same, all confirmed. So see you tomorrow morning with the talk by Alberto Cardona, 10 a.m. from Argentina time. I hope you are well, all parts of the world with this crazy schedule. I know for Mexican, they get up early at 7 in the morning, and the European are very late having dinner. So it's the only way to do it with this pandemic times. And thank you, everybody, for your contribution, for your question. Thank you, Juan Carretero, for constantly paying attention to the details. And thank you to all talks. See you tomorrow.
See you all tomorrow. See you.
Now I left. If you want to talk with each other view, I can left the open the Zoom meeting for maybe an hour. What do you want? If you could socialize and contact each other, I will left the room open.
I have to go out to have a lunch because it was a little.
Yes, I also we lost the break.
Because here is a holiday here, and so I have visiting here. People on the road. Vinicius could come in on time. It was on the road.